Hello and welcome to the full Go programming course. By the end of this video, you'll learn everything you need to start programming in Go. Developed at Google in 2009, Go, or also known as GoLang, was designed for simplicity, efficiency, and reliability. It combines the performance benefit of C and C++ with the ease of use of languages like JavaScript and Python. Today, it is used by tech giants and startups alike for web development, cloud services, and distributed systems. It is the language used to build powerful applications like Docker, Kubernetes, Terraform, and CockroachDB. Its simplicity and clarity make it the perfect choice for someone who wants to learn programming. For seasoned developers, learning it is more straightforward and it would look good on your CV. According to the latest Stack Overflow developer survey, Go developers, or as affectionately known as Gophers, make around $92,000 a year, which is not bad. No previous experience is required. This course is designed for learners of all levels. We'll start with the basics at a slow pace, then progressively cover more complex topics. I will also provide plenty of exercises to keep you engaged and boost your confidence. Towards the end, we'll build real-world projects to solidify your understanding and give you a taste of what it's like to be working with Go. We'll build a stock analysis tool to assist in picking stocks to trade and a REST API for serving stock news. I made all the code in the course available for you to try out. I've prepared an online platform where you can view, edit, and run the code right within your browser. If you have any questions or thoughts, feel free to leave them in the comments section below. I put a massive effort in creating this course, so if you find it helpful, please like the video and subscribe for more content. My name is Talal and I'm delighted to take you on this journey. Now, before we get to setting up your development environment, let me give you a quick overview of the key philosophies and objectives of Go. Go aims for simplicity in its syntax and language features, making it easier to read and write. The language designers intentionally left out many features found in other languages to keep the language simple and straightforward. Efficiency. Go is a compiled language, meaning your code is directly transformed into instructions that your computer's processor understands. Compiled languages tend to run faster because they speak directly to the hardware. This means Go programs start quickly and run efficiently, comparable to C and C++. However, unlike C and C++, Go has a garbage collector. Garbage collection is an automatic memory management feature that frees up memory space that is no longer in use by the program. With C and C++, it's the programmer's responsibility to manually manage memory. However, manual memory management is error-prone. Forgetting to free memory can lead to memory leaks, while freeing memory too early can lead to program errors. Concurrency. Concurrency is about doing multiple things at the same time. Modern processors, from smart gadgets to servers, all use multicore architectures to allow for concurrent processing. Go's concurrency model, based on Goroutines and channels, aims to make concurrency-related issues such as race conditions less prevalent and easier to manage compared to traditional thread-based models. Robustness and reliability. Go comes with a comprehensive and robust standard library. A library in programming is a collection of pre-written code that developers can use to solve common tasks, rather than writing everything from scratch. Go's standard library is extensive, covering a wide range of functionalities, from handling I/O operations, HTTP requests, to complex data manipulation. This rich set of tools makes Go not only powerful, but also practical, as it minimizes the need for external dependencies. To start working with Go, head over to this website, go.dev, and click the download button. Click on the installer for your operating system. I'm on Mac, so I'll pick the one for Mac OS. If you're on Windows or Linux, everything in this course will work exactly the same. This will download Go version 1.21.5, which is the latest at the time of this recording. There's a good chance there will be a newer version by the time you're watching this course. If so, you should download that version. From there, it's a standard installation process. If you're on Windows, you might need to add Go to your path variable. Next, we need to install an IDE, Integrated Development Environment. It's essentially a text editor with special features for software development. All of these IDEs will work, but my favorite is Visual Studio Code. So I'll just Google download VS Code and click on the first result. Again, I'll pick Mac. This isn't an installer, this is the app itself. So once it's downloaded, I can launch it immediately. To enhance our development experience, we'll download the official Go extension for VS Code by going here to the extensions panel and searching for Go. It's the first result with the most number of installs, so we'll install it. Lastly, go up to the View menu here on top and choose Command Palette. In the search box, search for install/update, and this should highlight the command go install/update tools. I'll click it and select all tools. The extension and tools enhance the development experience by providing things like code completion, auto-formatting of the code, and underlining syntax and compile errors. Now we're ready to create our first project. Go up to the File menu and click on Open Folder. It doesn't exist yet, so I'll create a new folder and name it Hello Go and open it. Go code lives in modules. To create a module, go up to the Terminal menu and click on New Terminal and type the command go mod init hello go. This will create a go.mod file, which we'll examine later in the course. Now to create our first Go source code, come up here and click New File and name it main.go. All Go code must live in files that end in the .go extension. Inside the file, I'll declare package main, then create a function main, which is the entry point of any Go program. And inside of it, greet yourself by doing fmt.println hello name. Now to run the program, I'll go back to the terminal and run the command go run ./main.go and hit enter. And there I see my greeting printed. A simpler way to run the command would just be go run dot, which is the way I'll be using moving forward. In this lesson, we're going to learn about variables and data types. Variables are a fundamental building block in pretty much any programming language. They're the basic means by which data is stored and manipulated in a program. Imagine a box where you can store something like a number, a letter, or even a whole sentence. In programming, a variable is like this box. It's a place in your computer's memory where you can store and retrieve data. Let's illustrate this with an example. Going back to our first program, let's type var agency string equal sign double quotes and inside the double quotes fast track. Var is a keyword in Go that's used to declare a variable. It's like saying I'm about to create a new variable. Agency is the name of the variable. It's like a label we use to refer to our variable. The word string is what's known as a data type or simply type. It specifies the type of data the variable agency can hold. In Go, string is a data type that's used to represent text. By specifying string here, we're telling the computer that agency will use to store a text. Go is a strongly typed language. This means whenever we create a variable, we must specify its type. And once created, that type cannot change later on. Equals fast track. This part of the statement is known as the assignment. The equal sign is used to assign a value to the variable. In this case, we're assigning the text fast track to the variable agency. Strings must always be enclosed within double quotes, otherwise the computer will think it's a variable and throw an error. Now putting it all together, when the line var agency string equals fast track is executed in a Go program, several things happen. The program allocates a space in memory to store a string. This space is labeled as agency, so whenever we use agency in our program, we're referring to this space. The program then stores the text fast track in this memory space allocated for agency. After this declaration, we can use this variable agency in our program to access the string fast track. For example, if you want to print this to the console, you could use fmt.println agency, which would output fast track. We can also use fmt.println like this. We first type welcome to, then comma, then agency. And when we run this, we get welcome to fast track. Notice that we didn't put agency between quotes like we did with welcome to. Well, because if we do, we will get the word agency printed as opposed to the value of the variable agency. Now, as an exercise, I want you to create a variable called name and assign your name as the value of the variable. And update this first statement to use the new variable to print hello, your name. Feel free to pause the video, try it, and come back later to see my solution. So to create a variable named name, we can do var name string equal Talal, which is my name. But an alternative way would be to use the short variable declaration. This is how it looks like. Name colon equals Talal. Using the colon tells Go that we're creating a new variable rather than assigning an existing one. And because the value is between quotes, Go knows the variable is of type string. This is called type inference. This is a concise and powerful syntax that is used the majority of the time. To use it in the greeting, we can update this statement and delete Talal here and the space 2. Add a comma after the closing double quotes here and add name. To add the exclamation mark, we can add a comma after name and add the exclamation mark. When we run this code, we see that we still get the same result as before, except for the space here before the exclamation mark, but we will see how to fix that in a bit. Now let's create a variable for the total number of cars available to rent. Var total cars int equals 50. This line declares a variable of the integer type. The variable name is total cars and we assign it the value 50. The int data type is used to store integer numbers. We can also declare numbers that contain a decimal point. A good use for that is to store a price. So let's declare starting price colon equals 29.99. Here, using the short variable declaration, we created a number that has a decimal point. Now, Go will declare this variable as type float64. Floats are floating point numbers, and they are used to store numbers with a decimal point like 29.99 or 37.35. Now let's print the message. Our prices start at, and then the starting price. This time we won't use println though. I want to show a different function. Printf. Here's how it works. fmt.printf. Our prices start at percent symbol v. This is called a placeholder. Then comma. Then we pass the starting price. And let's add another line. This time with println, saying take your pick. Now let's run this. We see our prices start at 29.99, then take your pick conjoined with it, which is not something we want. But that's because printf doesn't automatically add a line break or a space between arguments like println. Let's add a line break. We do that by adding \n to the end of the sentence. And when we run the code, we get the expected result. Now, as promised, let's fix the personalized greeting from earlier. Let's swap println with printf, and let's add the %v placeholder, then exclamation point, then \n for a new line break. And let's run this and see. We get a nicely formatted personalized message. Another very useful type is the bool, short for boolean. A boolean has the value true or false, and we use it for logical operations and decision making with the program. Let's create a variable that can be used to indicate if insurance is included. Var insurance included bool equals true. Or using the short declaration syntax, insurance included colon equals true. And we can also set it to false. And just like any other variable, we can print its value. In Go, when you declare a variable without assigning it a value, for example, by using the syntax var name data type, it is automatically initialized with a 0 value. These zero values are default values for various data types in Go. For string, the zero value is an empty string. For integers, the zero value is 0. For floats, the zero value is 0.0, and for booleans, the zero value is false. In this example, I declare a variable name of type string and I don't set its value. Then I go ahead and print it. And I do the same for count int price float 64 ensured bool. And when I run this code, indeed I get name with nothing printed, count 0, price 0.0, ensured false. Let's look at some things we can do with strings. Let's say we have the string hello world. We store it in a variable stir. We can then use the built-in function len to calculate its length like this. We declare a new variable length and give it the value len stir. Let's print the variable length and run the code. We get 13, which is the number of characters. We can actually pass len stir directly to println. This way the output of the length function is passed to the println function directly without needing to hold it in a variable. Moving on, say we have a variable stir1 which holds the string go programming, go in uppercase, and we have stir2 which holds go programming with go with the g lowercase. We can check if the strings are equal using the strings.equalFold function, and we pass stir1 and stir2. This function returns true if the supplied strings are equal. Let's use strings.equalFold as input to fmt.println, run the code, and we get true. This is because the equalFold function performs a case-insensitive comparison. So even though the first G is capital, but the second G is small, it still returns true because it's a case-insensitive in comparison. The package strings contains a lot of useful string-related functions. We can view any package's public documentation by clicking the package name while pressing the command on Mac or Control on Windows. This opens the web page containing the package's official documentation, as we can see here. The overview reads, package strings provides simple functions to manipulate UTF-8 encoded strings. The index here lists a bunch of functions. Here we can see equalFold that we've just used. Let's look at examples of using some of those. In this example, strings.index function finds the first occurrence of capital W in stir4, hello world, and returns its index. We capture the returned index in the variable windex and print it. If we run this code, we get 7. The index in a string refers to the position of individual characters within the string. String indices are zero-based, which means indices start with 0. This means the first character of the string is at index 0, the second is at index 1, and so on. If you look at the string hello, space, world, exclamation point, H is at index 0, E is at index 1, the first L is at 2, the second L is at 3, O is at 4, comma is at 5, space is at 6, and W is at 7. Hence, strings.index function returns 7 when we pass W to it. If we were to pass L, it would return 2 because it returns the index of the first occurrence. Also, we're not limited to individual characters. We can pass multiple. So if we were to pass the word hello, the function returns 0 because hello is at the beginning of the string. Finding the index within a string is important because we can use it to perform other operations, as we will see next. This example demonstrates string slicing. This line takes a slice of stir4 starting at index 7 and ending before index 12. We know the W is at index 7, So counting from here, 8, 9, 10, 11, 12. The exclamation point is at 12, so the slicing stops at index 11, effectively extracting the word world. Let's run this code. Indeed, we get world. This is called the slicing syntax. Slicing syntax in Go allows you to create substrings by specifying start and end indices. The start index is included in the new substring, while the end index is excluded. If the start index is omitted, it defaults to 0, the start of the string. If the end index is omitted, it defaults to the length of the string, including all remaining characters. Let's examine that with those two println statements. Stir4 colon 7. This slices stir4 from the beginning to just before index 7. And stir4 7 colon. This slices stir4 from index 7 to the end. If we run this code, we see that the first line produces hello, comma, and the second line produces world exclamation mark. Let's look at another function from the strings package. In this example, we declare a string stir5 and give it the value hello go. We then call the function strings.replace. We pass stir5, the string go, the string world, and 1. This replaces the first occurrence of go with world in stir5, hello go. The number 1 indicates that the function should perform only one replacement. If we run this code, indeed hello go becomes hello world. This is essentially similar to the find and replace functionality you find in text editors like Microsoft Word. Or even here in VS Code, you can access this functionality by pressing Command F or Control F in Windows. In this example, we declare stir6 and assign it Go programming, the Go and the P in uppercase. Then we have strings.toUpper stir6, which converts stir6 to uppercase. And we have strings.toLower stir6, which converts stir6 to lowercase. If we run this code, you see that we get Go programming all in uppercase. And in the following line, we get Go programming all in lowercase. This next function is a commonly used one. Strings.contains checks if a string contains another string. Using stir6 Go programming, strings.contains stir6, and we pass Go will return true, and strings.contains stir6 GoLang will return false. Let's run the code to confirm this. Indeed, we see that this is the case. String operations are fundamental in many programming tasks, like parsing text, formatting output, or handling user input. Please also note that strings in Go are immutable, meaning once a string is created, it cannot be changed. Operations like concatenation, trimming, replacing, or changing case always return a new string. So the output of each of those functions is always a new string, but it never modifies the existing string. The strings package provides a rich set of functions to work with strings, making it easier to perform these tasks. Feel free to go over the documentation of the strings package to learn more. It's a good idea to familiarize yourself with documentation of this type, because many times it will be the place to go to if you have any doubts about the functionality of a function or how to use a certain package. The documentation follows a standard format, so it looks familiar no matter what package you're looking at. I now want to shift gears to numeric unsigned, which numeric types in Go can be categorized into three categories: or positive integer types, floating point types, size, and complex number types. We've seen the int type, the maximum value many variations of the integers that have their special use cases. First, there's uint8. Let's create one here. Var tiny uint uint 8. The U is for unsigned, which means it can only be used for 0 or positive integers. 8 refers to its size, which is 8 bits. It means the maximum value we can assign to it is 255. And let's give it the value 200. Looks okay. Now let's try to change the value to 256. Immediately, we get a red squiggly line underneath the value indicating an error. Also, if we try to assign a negative value like -1, we get a squiggly line. Similarly, uint16 is for integers between 0 and 65,535. Then there are uint32 and uint64 with these maximum values. If you need an integer that can be set to negative values, then you can use one of the integer types. Int 8 has a size of 8 bits and it can be set to any value between -128 and 127. Int 16, int 32, and int 64 has these value ranges respectively. Now for the floats, we have float 63 and float 64. The numbers 63 and 64, they refer to the bit size of the float. A float 32 type, often referred to as a single precision floating point, uses 32 bits to store the value. It provides an approximately 6 to 9 decimal digits of precision. The maximum value a float 32 can represent is about 3.4 multiplied by 10 to the power 38. On the other hand, a float 64 type, often referred to as a double precision floating point, uses 64 bits. It provides about 15 to 17 decimal digits of precision. The maximum value of float 64 can represent is about 1.8 multiplied by 10 to the power 308. Complex numbers can be represented by either complex 64 or complex 128 types. Complex 64 can be used for complex numbers with float 32 real and imaginary parts, while complex 128 can be used with complex numbers with float 64 real and imaginary parts. Now that we know more about numeric types, let's see some basic math operations. In this first example, we would like to convert temperature between Celsius and Kelvin. The temperature in Kelvin equals the temperature in Celsius plus 273.15. Let's first declare an integer variable, temp C, and assign it 32. And let's create one for the temperature in Kelvin. We know that the temperature in Kelvin might have a decimal point, so let's make it a float. Temperature K colon equals 0.0. The fact that we initialize it 0.0, the U is for the Go compiler to know that we mean means float 64. It can only be used for hover over here or positive integers. Indeed, it says 8 refers to its size, float 64, which is 8 Now let's set the temperature in K. It means we do the maximum value we can assign to it just like we would on a piece of paper. Temperature K equals temperature C plus 273.15. However, notice that we now have a red squiggly line underneath 273.15. If we hover over 273.15, the error says 273.15 between parentheses untyped float constant truncated to int. Basically, we get this error because we're trying to perform an arithmetic operation between an integer, temperature C, and a float, the number 273.15. We can solve this issue in one of two ways. The first is we perform something called a typecast, which means temporarily converting a type to another type. This is how it would look like. We type float 64, then parentheses, and in between the parentheses, we put temperature C. Now the error disappears. What this does is convert the integer to a float and creates a new variable to hold the value. This variable is only used for this operation and will not affect the type of temperature C. Temperature C will always be an integer. Let's remove this float64. Of course, we get the red squiggly line again. The other way to solve this error would be simply to change the type of temperature C to a float64. And we can do this by adding a decimal point and 0 to 32 here. Now temperature C is 32.0. This is enough to tell the compiler that temperature C is a float64. And as we can see, the error has disappeared. Then let's print the temperature in C and the converted temperature in K. Let's run the program. We get temperature in Celsius 32, temperature in Kelvin 305.15. Now, an exercise for you. Write code that converts 273 Kelvin to Celsius. This is the equation for the conversion. Feel free to pause the video and try this out yourself. The solution is quite simple. Let's define a variable temperature K colon equals 273.15, and this time let's declare temperature C and assign it in the same statement using colon equal temperature K minus 273.15. Let's print both temperatures and run the program. We get temperature in Kelvin 273.15, temperature in Celsius 0, as expected. Now let's see how to convert a Celsius to a Fahrenheit. This is the conversion equation. Let's first declare temperature C using the short declaration syntax and assign it 16. Now let's create a variable temperature F and assign it the value of the equation. Temperature C multiplied by 9 divided by 5. We use the asterisk for multiplication and we use the forward slash for division. Then we add 32. Let's print both temperatures and run the code. We get temperature in Fahrenheit 60. Now, if you're following along with the calculator, you'd know that the answer is actually 60.8. So why are we getting 60 here? Well, let's hover over temperature F here. We see that in fact it's an integer. That's because temperature C is an integer and 32 is an integer constant. We could declare temperature F as float separately like this and just make this an assignment statement. But now we get a red squiggly line under the rest of the statement. You could probably tell by now that this is because temperature C is an int while 9 over 5, which equals 1.8, is a float. To fix this, we can change temperature C to be a float by just updating 16 to 16.0. Now when we run this code, we get 60.8 as expected. Next, we'll convert a Fahrenheit temperature to Celsius using this equation. Let's start by declaring temperature F and assigning it 59.0. Then we declare temperature C and assign it temperature F minus 32 multiplied by 5 over 9. Let's print both temperatures and run the code. We get temperature in Celsius 42, which is all kinds of wrong. We should have gotten 15. Well, from mathematics, we know that according to the order of operations rules, multiplication and division are performed before addition and subtraction. So in this statement here, 32 is multiplied by 5, which equals 160. 160 is then divided by 9, which equals 17.8. 17.8 subtracted from 59 equals 41.2. I'll leave it as a quiz for you to figure out why we got 42 when we run the code. Let me know in the comments if you figured it out. Now, fixing this is very easy. Order of operations states that parentheses precede even multiplication and division. So, to correctly write the formula, we place temperature F minus 32 in between parentheses and rerun the code. Now we get 15 as we should. Another exercise for you. Write the code that would convert 288.5 Kelvin to Fahrenheit and 70 Fahrenheit to Kelvin. This is the formula. Feel free to pause the video and try it out yourself and come back for my solution. Well, this is a lot simpler than it looks. Looking at this formula, we can see that it converts Kelvin to Celsius first, then converts the Celsius to Fahrenheit. So we can just reuse the code we've written in the previous tutorials. Let's first define temperature K and assign it to 88.15. Then define temperature C and set its value from the equation we used earlier. Then from the previous tutorial, we know how to get Fahrenheit from Celsius. So we just paste that code here. Let's print both temperatures and run the program. We get 59 Fahrenheit, which is expected. And to convert from Fahrenheit to Kelvin, we follow a similar approach. First, we define temperature F, assign it 70.0, then temperature C, and convert from Fahrenheit, like in the previous tutorial, then to Kelvin, like the tutorial before that. And let's print both temperatures and run the code. Indeed, we get 294.261 Kelvin as expected. In this tutorial, we're going to look at some math functions from the math package. Let's declare temperature C float and assign it the value 12.75. We can use math.round function to round the float number to the nearest integer, rounding halfway from 0. Let's print the original value and let's print the rounded value. Let's run the code. We can see that 12.75 was rounded up to 13. If we change the temperature to say 12.15 and rerun, we get it rounded down to 12. Another rounding function is math.ceil, short for ceiling, which returns the least integer value greater than or equal to the float number. So if you want to always round up, you use the math.ceil function. Here we call math.ceil with 12.5 and run the code. We get 13. Even if we change the value to 12.01, we still get 13. The opposite can be achieved with the math.floor function, which rounds the float down. So if we use math.floor and pass 12.99, we get 12. Let's quickly look at some other functions from the math package. Math.ups returns the absolute value. Here we get 5.5 when we pass negative 5.5. Math.pow accepts two parameters and returns the result of the first to the power of the second. Here we call math.pow with 3 and 2. We get 9, which is 3 to the power of 2. Math.squared returns the square root. Here we call it with 16 and we get 4. There are also trigonometric functions, for example, sine and cosine, as well as exponential and logarithmic functions. As with the strings package, you can read the documentation for all functions available and how to use them. In this course, as we look at various packages and their numerous functions, keep in mind that it's not necessary to memorize every little detail. For example, if you need to find the maximum of two numbers in Go but aren't sure how, a quick Google search like find max of two numbers in Go usually does the trick. You'll likely find that the max function from the math package is what you need, along with some handy code examples. So don't stress about memorizing functions or syntax. Focus on grasping the concepts. Proficiency in the detail will naturally follow with practice. We've seen how we convert an int to a float using float64 and passing int. You might have noticed that even though the variable temp float is of type float, when we print it, we get 10 rather than 10.0. In fact, even if we call println with a hard-coded 10.10 and run the code, we still get 10. Well, that's because the fmt.println function formats floating point numbers in the most compact and readable way. So if the decimal part of the number is 0, as in 10.0, it is omitted when printed, and we only see 10 instead of 10.0. If we want to see the decimal part, we'd have to use a format specified with fmt.printf, like this. %sign dot 1f here specifies a decimal point with 1 digit after it. If you wanted 2 digits after the decimal point, we'd have to do %.2f. If you're ever in doubt and you need to know the type of a variable, you can do this. fmt.printf %T, and then we pass the variable. So if we pass temp int and on the code, we get int, which is indeed the type of temp int. And if we pass temp float, we get float64, which is indeed the type of float64. This is very handy when debugging. Now, to convert an integer to a string, you might be tempted to do something like this. String, say 1 to 3. Okay, let's try this out. Let's declare var stir and assign it stir parentheses 1 to 3. And let's fmt.println stir. Before we even run the code, we get this warning squiggly line here, but let's run the code anyway. We get an opening curly brace. Weird. Let's try another number. Maybe 80. When we run the code, we get a capital P. Obviously, this isn't what we're after, so what's going on here? Well, if we hover over the string function here, it says conversion from untyped int to string yields a string of 1 row, not a string of digits. Did you mean fmt.sprint? Okay, let's try fmt.sprint instead of string. Let's replace string 1 to 3 with fmt.sprint and on the code. Yep, that works. And just to confirm, let's print the type of stir here. Sure, it's a string. That's perfect. But what was that rune thing? Well, rune is an alias for int32. It's just an alias, so it means a rune is actually an int32 type. And it's used to handle individual characters in a string. In other programming languages, strings are made up of characters. In Go, the concept of a character is called a rune. A rune is an integer that represents a Unicode code point. What's a Unicode? Unicode is a standardized set of characters that includes almost every character from every writing system in the world, along with many symbols and special characters. So, when we did string 1 to 3, we got the string character behind the rune 1 to 3, the curly brace. This is useful in some situations, as we will see later on in the course, but it's not what we wanted here. Another way to convert an int to a string is by using the i2a function from the strconv package. This is how. And if we print this variable, we sure get 10 as a string. Package strconv implements conversions to and from string representations of basic data types. Here, we have a string containing the number 42. To convert it to an int, we call the function strconv.a to I. The first return of the function is the converted string. Let's print it and run the code. Sure enough, we get an int. We can verify that this is an int by printing its type, like I showed you earlier. And let's run this. Sure enough, we get int. To convert a string to a float, we use the parseFloat function. Here, we have a string containing the float 3.14159. To convert it, we call strconv.parseFloat on this string. Let's print it and run the code. Sure enough, we get a float. Let's look at another function from this package. strconv.parseBool. Before we do anything, let me just hover over the function here. It says it accepts 1, small t, capital T, true, all capital, true, all small, true with a capital T, 0, small f, capital F, false, all capital, false with a small f, false with a capital F. What this means is it accepts any of those values, and if we're passing any value from the first set here, it will parse it to true, and if any value from the second set here, it parses it to false. This is very useful, especially if you're parsing a value returned by an API created using a different technology. Let's test this with just small t and print the result. Sure enough, we get true. The underscore is a blank identifier that lets Go know that we're not going to use this value. Otherwise, if you declare a variable and not use it, the compiler will scream at you. There are situations where you need to declare a variable to be used throughout the application, but the value of that variable doesn't change. For example, variable agency doesn't need to change throughout the program. It is not variable, rather it is constant. If a value is fixed and doesn't need to change throughout the program, it is best declared as a constant. Constants in Go are declared using the const keyword, and once a constant is defined, its value cannot be altered later on. Here's how to declare a constant in Go. Use the const keyword followed by the name of the constant, in this example, agency, then the type of the constant, string, then the equal sign, and then the value of the constant. You could also omit the type of the constant, which would lead to its type being inferred from its value. Just like how vars can be inferred when using the short variable declaration. If you have multiple constants, you can group them together like this. Just type const, then between parentheses, declare all your consts. This is handy and it's a clearer way of grouping together logical constants. Then there is iota, which takes constants in Go into a new level. Iota in Go is the pre-declared identifier used to create successive integer constants. Here's an example. We have a set of constants representing rental car categories. We define a const block with parentheses just like before, but now we set the value of the first const to iota. This leads to economy to equal 0, compact equals 1, standard equals 2, full size equals 3, and luxury equals 4. And if you wanted a certain value to be skipped, for example, if you want the sequence to start with 1 rather than 0, then you assign underscore to the first iota value like this. Now economy becomes 1, compact becomes 2, etc. This is a common use case for iota, especially if you're mapping an enum to a database lookup table. Iota makes constants in Go much more powerful and efficient. Now let's make our program a little more interactive by asking the user to enter their name. One way of accepting a user's input from the command line is by using the fmt.scanln function, like this. Let's first print the message, what's your name? We then declare var name string to hold the name the user enters. Then, this is how we use scanln function to wait for the user's input. fmt.scanln. Then, before we pass name, we type the ampersand symbol, then we pass name. Let's print a customized greeting and let's run the program. I'm going to type Talal, then we get hello Talal. Besides showing you how to accept the user's input, I intended this tutorial to be an intro to one of the most important topics in Go, that ampersand symbol. This is called a pointer, and ampersand name is pointer to name. In Go, pointers are used to hold the memory address of a variable rather than the variable's value itself. What does this mean? Well, earlier in the course, we said that a variable is like a box or a place in your computer's memory where you can store and retrieve data. Well, a pointer is like an address tag or a label that has a location of one of those boxes. Instead of holding the actual item, it holds information on where to find the box. In computer terms, this address tag is called a memory address. Why use pointers? Well, let's look at our scanln function here. The function takes the memory address of the name variable, reads the user input, and writes it in that memory address. That's how we can get the value even though the variable is declared outside of the function. I'll give you another example to make this clearer, but first let's look at how we declare and assign a pointer. To declare a pointer, you use an asterisk before its type. So this line, var my string pointer asterisk string, is saying we are declaring a variable named my string pointer, and its type is a pointer to a string, not a string, a pointer to a string. This is not the same as the declaration var my string string. To assign a value to my string pointer, we can't assign a normal string like this. This won't work because this would be assigning a string to a pointer to a string. What we have to do is add the ampersand sign in conjunction with another variable that is of type string, which is what we've done with the scanln function. Now to the example. Here we have a function say hello that accepts a string argument and sets it to hello world. We have another function that instead of a string accepts a pointer to a string. It then sets the value pointed to by this pointer to hello world. We will discuss functions in great detail at a later lesson. This is a small example to explain pointers. Now to use these functions, we create a variable greeting hello, go. We pass this variable to the first function say hello, then print it. We then use the ampersand symbol just like we did with the scanln function and pass it to the second function say hello pointer. Then we print greeting. Let's run this code. The initial value is hello, go. After calling say hello, the value is still hello go. So that means the value is unchanged by the function call. On the other hand, after calling say hello pointer, the value is now updated to hello world. Here's what happened. When we call the say hello function, Go creates a brand new copy of greeting and passes it to say hello. And inside say hello, it is the copy that gets updated to hello world. On the other hand, when we call say hello pointer with the address of the variable greeting, inside say hello pointer, Go updates the value of the greeting variable itself. Using the address, Go accesses the memory location of greeting and writes hello world in that memory location. I admit that this concept might be a little bit complex at first, but we will revisit this in greater detail later in the course when we discuss methods, and that will make it much clearer. So let me ask you this. What is the zero value of a pointer? We know that for strings, integers, floats, and booleans, the zero values are empty string, 0, 0.0, and false. But what's the zero value of a string pointer, an integer pointer, float pointer, or a boolean pointer? The answer is nil. Nil is a special value that represents the absence of a value. For a pointer, nil means it points to nothing. It is the default state of a pointer before it's assigned to an object. To demo this, let's create a new pointer var string ptr, short for pointer, asterisk string, var int pointer, asterisk int, var float pointer, asterisk float64, var bool pointer, asterisk bool. We won't assign any of them. We'll just print them and run the program. We can see that the value of all these is nil. Nil is the zero value for several types, not just pointers. We will see those as the course unfolds. Conditional operators are what allows programs to have complex behaviors and behave differently in different situations. We want to design a sign for a highway that displays you're going too fast when someone is speeding and thank you for not speeding otherwise. Let's begin by declaring a new variable is fast and initialize it to true. Next, let's add this. If is fast, opening curly brace, and we see that VS Code automatically creates a closing brace for us. Then print you're going too fast, slow down. Just run this. Sure enough, we get you're going too fast, slow down. Now let's set is fast to false and rerun the program. No surprise, we don't get any output. To print a positive reinforcement message, let's come here and add else. Again, opening curly brace, new line, and let's print thank you for not speeding. Let's run this. Sure enough, we get thank you for not speeding. We're now going to enhance our highway sign with additional functionality. It will not only warn drivers when they are speeding, but also when they're driving too slow. First, we add a new variable is slow and initialize it to true. Now let's update our if statement. After the if is fast block, let's add an else if statement here. So else if is slow, you're going too slow, this is dangerous too. Let's run this program. Sure enough, we get a slow warning message. But what if the driver is neither driving too fast nor too slow? Well, for this, we add an else block like before. Let's type else, opening curly brace, then print thank you for driving within the speed limit. Let's change is slow to false and rerun the program. We see that it thanks for the driver for maintaining the speed limit. Let's improve our highway sign so that it can respond based on the actual speed of the vehicle. We start by defining two constants, upper speed limit and lower speed limit. We set the upper speed limit to 120 and the lower speed limit to 80. Now, let's introduce a variable named speed. And for demonstration, we'll set it to 130. Now, our if statement, if speed greater than sign upper speed limit, we print you're going too fast, slow down. But what if the driver is going too slow? Well, else if speed less than sign lower speed limit, open the curly brace, new line, print you're going too slow. This is dangerous too. Lastly, we add an else block to handle the situation where the driver is within the speed limit. Let's print thank you for driving within the speed limit. Okay, let's run this. We get you're going too fast, slow down. Because speed, which is 130, is greater than upper speed limit, which is 120. Now let's set speed to 70 and rerun the program. We get you're going too slow, this is dangerous too. Now let's set speed to 110 and run the program. We get thank you for driving within the speed limit. Now we're going to check if the driver is exactly at the upper or speed limits and provide specific feedback. Let's come up to the first if block here and check if speed is exactly equal to the upper speed limit by using the logical operator double equals. This is how we check for equality. If we were to use a single equal sign, we get a compiler error saying expected Boolean expression found assignment, because the equal sign is used for assignment but not for checking for equality. So if speed equals upper speed limit, we want to print you're driving at max allowed speed, be careful. Now check if speed is exactly equal to lower speed limit and warn the driver that they're driving at the lowest speed limit. We just add else if speed equals lower speed limit and print a message, you're driving at the lowest allowed speed, be careful. Now let's set speed to 120 and run the program. Sure enough, we get you're driving at max allowed speed, be careful. And let's set speed to 80 and run the program. Sure enough, we get you're driving at the lowest allowed speed, be careful. Now let's say we want to get stricter with our speed limit checks and issue a warning even if someone is driving at the speed limit. So if someone is driving at the speed limit or greater than the speed limit, we want to issue a warning. Only if you're driving below the speed limit, then you're fine. To do this, first we check if speed is greater than or equal to upper speed limit by using the operator greater than followed by equal. Similarly, let's check if someone is at the lower speed limit or lower using the operator less than followed by the equal. Else, we print a positive reinforcement message. To test this, let's set the speed to 120 and run the code. We get you're driving too fast, slow down. Let's set it to 121. We get the same message. Now let's set it to 119. We get thank you for driving within the speed limit. Now let's set it to below the speed limit, 75. We get you're going too slow, this is dangerous too. Now let's set it to exactly the lower speed limit, 80, and run. We still get you're going too slow, this is dangerous too. Logical operators allow us to combine multiple conditions in sophisticated ways. We will determine what type of day it is based on two conditions, whether it's a weekend or a holiday. We start with two Boolean variables, is weekend and is holiday, both initially set to false. First, we check if it's both a weekend and a holiday using the logical operator AND. We use two ampersand symbols. Then we print it's a holiday on a weekend. So here we have a combined condition, and this condition will only be true if is holiday is true and is weekend is true. If one of them is false, then the whole condition becomes false. Next, let's use an else if to check if it's a weekend but not a holiday, and we do this using is weekend and using the two ampersands. To say is not a holiday, we use the exclamation point before is holiday. This exclamation point is called the not operator, and it basically inverts the condition. So when you use not, false becomes true and true becomes false. So for this condition to be true and this message to be printed, is weekend needs to be true and is holiday needs to be false, because with the not operator, false becomes true and true becomes false. And with the AND operator, we want both conditions within the AND to be true. Then we check if it is not a weekend, but it's a holiday. Pause the video for a moment and think about how we would write it. We type else if not is weekend and is holiday. If that's the case, we print it's a weekday but a holiday. So again, for this condition to become true, is holiday needs to be true and is weekend needs to be false, so that not false is true, so that we get true and true, and then we print the message. If none of those conditions apply, else print it's a regular weekday. Now let's test the program with both is weekend and is holiday set to false. Of course, we get it's a regular weekday. Let's take it logical condition by logical condition. In the first case, is weekend is false, so the compiler won't even look at is holiday. We said with an AND, all conditions in the logical operator need to be true. So since is weekend is false, this whole condition will never be true and we don't need to bother with it. And the same can be applied for the second line. Is weekend is false, no need to bother with the other operands. Even though not is holiday becomes true because is holiday false, so not false true, but because we have false and true become false. The third, not is weekend, now this is true because is weekend is false, so not false is true, and is holiday, well this is false because is holiday is false, so this whole condition is not satisfied. Because all three conditions are not satisfied, we fall into the else statement. Now, the next test case, let's set is weekend to true and keep is holiday to false. First condition is weekend true, but is holiday false, so this condition is not satisfied. The next line is weekend true and not is holiday. This is true as well. Is holiday is false, so not is holiday true. So when we run this, we should get it's a regular weekend day. Let's run. Sure enough, we get it's a regular weekend day. Now let's flip it. Let's set is weekend to false, but is holiday to true. First condition, not satisfied. Second condition, is weekend is false, so we won't even look at the second condition. So the whole condition is false. The third condition, not is weekend, this is satisfied because is weekend is false, and is holiday is true. So when we run the code, we will get it's a weekday but a holiday. Let's run the code. Sure enough. Lastly, let's set it is weekend to true as well. So now is weekend and is holiday are true, and the first condition is satisfied. Is weekend true and is holiday true? True and true become true, and when we run this, we should get it's a holiday on a weekend. When we run it, sure enough, that's what we get. This example demonstrates how logical operations can be used to create complex conditional statements. Before moving away from logical operators, I want to show you a common way of declaring and assigning Boolean variables. This line creates a new variable is day off based on is weekend and is holiday using a new logical operator or. What this line means is day off will be created as a boolean and its value will be true if is weekend is true or is holiday is true or both of them is true. So unlike the logical operator and, only one operand needs to be true for the condition to evaluate to true. So this is a new way of declaring boolean variables. The compiler first evaluates the condition is weekend or is a holiday, and the value of that is assigned to is day off. In this case, since is weekend is true, is day off also becomes true, regardless of is holiday. So now we can use is day off in an if statement. If is day off, println it's a day off. And we can do the same with the logical AND operator. First, let's set is holiday to true, and in the next line, is holiday weekend is declared and set to the result of is weekend and is holiday. And since both is weekend and is holiday are true, is holiday weekend becomes true. And in the if statement, we use the new variable to check for a holiday weekend. We can also use comparison operators to declare and set a boolean variable. Here we declare is speeding and set it based on the comparison of speed and upper speed limit. If speed is greater than or equal upper speed limit, speeding is true. Otherwise, it's false. So let's run all of this code. We get it's a day off because is weekend is true. Then we get it's a holiday weekend because here we set is holiday to true, and is holiday weekend is the combination of both is weekend and is holiday. And we get you're going too fast, slow down because our speed is 130, which is greater than upper speed limit. From this, we can see that we can create new Boolean variables based on logical operations as well as comparison operations. In fact, any statement that can lead to true or false can be used to set the value of a Boolean variable. The switch statement is a control structure used to execute different actions based on different conditions. Let's see this in action with a simple program that interprets color meanings. We start with the variable color set to blue. We then use a switch statement to evaluate the value of color. The switch checks the value of color against several case statements. This is how we write it. We type switch, then the variable color, then an opening curly brace. The first value we check against is red. We do this by typing case red colon. After the colon, we do the action. In this case, print red, passion, and energy. What this means is if the color equals red, we will print red, passion, and energy. Similarly, we can check for green using case green colon print green, growth, and harmony. And if blue, case blue, print blue, calm, and trust. And lastly, for yellow, case yellow, print yellow, optimism, and happiness. And for anything else, we use the keyword default, which is kind of equivalent to else in an if statement. Default, print unknown color. Now let's run the code with color set to blue. And sure enough, we get blue, calm, and trust. Let's update color to yellow. Run the code. We get yellow, optimism, and happiness. And if we try to set color to any color that's not part of our switch cases, like for example white, and run the code, we get unknown color. This switch statement efficiently handles multiple conditions, making the code more readable and organized comparing to a series of else-if statements. Let's look at another example of using the switch statement. We want to determine whether a given day is a weekend or weekday. We begin by creating a variable day set to Tuesday. Using the switch statement, we can check the value of day. The first case groups Monday, Tuesday, Wednesday, Thursday, and Friday together. If day is any of these, it prints weekday. This demonstrates how switch cases can be used to match multiple values in a single case. Now, the second case is for weekend days, Saturday and Sunday. If day matches either of these, we print weekend. Lastly, if day doesn't match any of the above cases, the default case is executed printing invalid day. Let's run the code. We should get weekday. Let's set day to Thursday and run again. Again, we get weekday. Now let's set it to Saturday and run. We get weekend. I now want to show you a slightly different form of switch. Unlike previous examples, this switch doesn't evaluate a variable directly. Instead, it uses conditions in each case to determine which block of code to execute. This code categorizes a person's life stage based on their age. We start with the variable age set to 25. Then we just have switch, this time without following it with any variable. And then immediately we have the opening curly brace, and our first case checks if a person is a minor. We do case age less than 18 colon fmt.println minor. The second case checks if the age is greater than or equal to 18 and less than 60. In this case, we print adult. The third and last case checks if age is greater than or equal 60. In this case, we print senior. Let's run the code. We get adult. Since 25 is between 18 and 60, it falls under the second case. And if we set age to 10 and run, we get minor. And for good measure, let's set age to 63 and run. Sure, we get senior. I want to show you another cool feature of the switch statement. We will display access permissions based on the user's role in an online blog where an admin has full system access, can publish content, can write content, and can of course view content. An editor has a lower access level. He can publish content, write content, and can view content. A contributor has an even lower access level and can write content and can view content. Lastly, the viewer has the least privileges and can only view content. And if someone has none of these roles, then they have no access at all. To do this, we start with the variable user role, and let's just initialize it with editor. First, we print the formatted message that states the user's role and indicates that we are about to list the access permissions for that role. The switch statement then checks the user role. Each case corresponds to a different role: admin, editor, contributor, and viewer. The first case checks if user role is admin. If so, it prints full system access. The all through keyword then tells the program to continue to the next case without checking its condition. So the next case will be executed no matter what. The next case is editor, which matches our user role. It prints can publish content and then falls through to the next case. For contributor, it prints can write content and again falls through. The viewer case prints can view content, but since this is the last case before the default, we don't have a fall through here because we only want the default to execute if none of these conditions match. Let's run this code with user role set to editor. As expected, we get can publish content, can write content, and can view content. Let's try it with admin. Sure enough, we get has full system access, can publish content, can write content, and can view content. And let's try with the contributor. We get can write content and can view content. Let's try with the viewer. Of course, we only get can view content. And if we try something else like guest, we get no access. So with each user role, we get a cascading list of permissions, starting from the role and including all roles below it. We're now ready to implement our first small project. We want to use everything we've learned so far to create a temperature conversion program. The program prompts the user to enter a numerical temperature value. The user is then asked to specify the unit of temperature they just entered. This can be C for Celsius, F for Fahrenheit, or K for Kelvin. The program then asks for the unit to which the user wants to convert their temperature. These two can be any of the three units, C, F, or K. Based on the current and target units provided, the program applies the conversion formula we used earlier in the course. The program should calculate and display the converted temperature in the chosen unit. formatted to 2 decimal places for precision. Feel free to pause this video and work on a solution yourself and then continue to see my solution. We start by declaring a temp variable of type float64 to store the temperature value and 2 string variables from unit and toUnit to store the current and target temperature units. We print enter temperature to prompt the user to enter the temperature value, and we use fmt.scanln to read it into temp. Next, we use the same technique to ask the user for the current unit of the temperature, and we can give a hint about acceptable values. C for Celsius, F for Fahrenheit, and K for Kelvin. fmt.scanln to read it into from unit. When dealing with user input, it's often a good idea to normalize the input to a standard format. So here we convert the value that the user enters to uppercase to ensure consistency in the comparison. So if the user enters a lowercase or an uppercase, the program will behave the same. Next, we ask for the unit to convert to and use scanln to read it into toUnit. And again, we convert it to uppercase. Next, we declare and initialize converted temp to 0.0. So converted temp is of type float64 and it will hold the converted temperature value. The switch statement then checks from unit to apply the appropriate conversion formula based on toUnit. If from unit is C, we check toUnit. If it's F, we convert Celsius to Fahrenheit. If it's K, we convert Celsius to Kelvin. The next case is for F, Fahrenheit. If from unit is F, we do a similar check, and if toUnit is C, we convert to Celsius, else if toUnit is K, we convert to Kelvin. The last case is for Kelvin, and again, based on toUnit, we either convert to Celsius, or if toUnit is F, we convert to Fahrenheit. Finally, we print the converted temperature along with the target unit, formatted to 2 decimal places. Notice the use of %sign dot to F to specify 2 decimal places. In programming, loops are fundamental constructs that allow you to repeat a block of code multiple times, either for a fixed number of times or until a certain condition is met. In Go, the for loop is the only loop construct, but it's quite versatile and can be used in various ways to mimic the behavior of while and do while loops from other languages. A typical for loop in Go has 3 components. Initialization. This is where you initialize your counter. This part executes only once at the beginning of the loop. Condition. The loop continues to execute as long as this condition is true. Post statement. This is usually an increment or decrement statement executed at the end of each iteration. For example, we have this simple for loop for I colon equals 0. This is the initialization. This is just a counter named I and starting at 0. Next, I less than 5. This is the condition for keeping the loop going. It's the loop's way of asking, am I still below 5? If the answer is yes, the loop keeps rolling. I++, that's the increment part. After each loop iteration, we add 1 to I. Inside the loop, we've got fmt.println simple loop iteration I. And this is where the action of the loop happens. Each time the loop runs, it prints out simple loop iteration followed by the current value of I. So if we run this, we'll see a line for each I from 0 up until 4, because we start at 0 and we stop just below 5, which is 4. Now let's write a loop that starts from 0 through 9 and prints odd numbers. It's like in the previous example, Let's start by initializing a loop variable j to 0. The condition is j less than 10 and the increment is j plus plus, meaning increment by 1 after each loop. Now, to check if a number is odd or even, we use this syntax j mod 2. The percent sign here is the modulus operator, which gives the remainder of a division. So this if statement checks if the remainder of j divided by 2 is 0, which is true for an even number. So if this is an even number, what do we do in this case? We use the keyword continue. The continue statement is crucial here. When invoked, it immediately skips the remaining portion of the loop's body and proceeds to the next iteration. So when j is an odd number, the condition j mod 2 equals 0 evaluates to false. So the continue statement is not executed. The loop then executes the next line. It's printing fmt.println odd number j, which print out the current value of j. Now let's run this code. We see odd number 1, odd number 3, all the way to 9. The continue statement is very useful for controlling loops behavior, and you'll see it all the time. Another very important way to control a loop's behavior is the break statement. Let's look at it using this example. Notice here that unlike the loops we've seen so far, this for loop has none of the three components, initialization, condition, or post. We only have for, then opening curly bracket. We print infinite loop iteration I. Next, we increment the loop counter by 1. This is called an infinite loop. If we let this run, it will keep going forever, consuming the computer's processor and memory. And just to show you, I'm gonna run the program, then quickly interrupt it using Control C. We reach this insane number of iterations. Now imagine if this was left to run freely. It would just keep going. Now, to break out of the loop, we use the break keyword. Let's come here after the print and check if I equals 3, break. The break statement causes the program to exit the loop immediately and not execute any subsequent code. So, the continue statement causes the loop to go to the next iteration, but the break causes the loop to exit altogether. Almost all programming languages have while loops, but remember, Go aims for simplicity and clarity, which is why it uses the for loop as a form of a while. Let me show you how. Just like in the previous example, we start by initializing the loop counter outside of the loop, but this time the for loop has a condition and it is set as y less than 3. This means the loop will continue to execute as long as y is less than 3. It's the key condition that controls how long the loop runs. Inside the loop, we have fmt.println, for loop as a while loop, iteration. Then there is an increment operation, y++ to increase the value of y by 1 each time the loop iterates. This is necessary for ensuring that the loop eventually ends. Without this increment, the loop will continue indefinitely since y would always be less than 3. The loop continues to run, printing values of y and incrementing it until y reaches 3. At that point, the condition y less than 3 becomes false and the loop terminates. And if we run this code, we see the line printed 3 times as expected. Right, it's time for our second mini project. This time we're gonna try something fun and cool with a classic game of rock, paper, scissors. The game is set up to be played in 3 rounds. This means the player and the computer will face off 3 times. In each round, the player is prompted to enter their choice, rock, paper, or scissors. The computer randomly selects its choice. The game compares both choices to determine the winner of each round. Rock crushes scissors, rock wins. Scissors cut paper, scissor wins. Paper covers rock, paper wins. If both the player and the computer choose the same, it's a tie. Feel free to pause the video and try this out yourself, making any assumptions and try it however you like, then come back and continue to see my solution. Also, feel free to share your solution in the comments below. Even if it doesn't work, don't worry about it. You'll learn better by trying. Now to the solution. We first define a constant rounds and set its value to 3. The game starts by printing, let's play rock, paper, scissors. You have 3 rounds. The game then enters a loop that runs for the number of rounds specified, 3. Now, the next line is interesting. Here, we're using the int n function from math/rand package and passing rounds to it. And if we hover over the function here to read its documentation, it reads int n returns as an int non-negative pseudo-random number in the half-open interval 0 n from the default source. What this means is int n will return a pseudo-random number between 0 and 3. This is very important because this is how we randomize the computer's choice. We store the random number in a variable computer choice num and use it to determine the computer's choice. 0 for rock, 1 for paper, and 2 for scissors. The switch statement maps these numbers to the corresponding string values. The player is then prompted to enter his choice of rock, paper, or scissors. This input is captured and stored in the player choice variable. We then print the computer's choice to the console, revealing what it chose for that round. The game logic is implemented using a switch statement to compare the player's choice with the computer's choice. And based on the rules of rock, paper, scissors, the winner of the round is determined. The first case checks if the player's choice and the computer's choice are the same. In this case, it's declared a tie. The next case checks if the player's choice beats the computer's, following the game's rules. Notice how we construct the case statement here. Case, player choice equal rock and computer choice equal scissor, comma, player choice equal paper and computer choice equal rock, comma, player choice equal scissors and computer choice equal rock. Remember, from the case statement, listing the case conditions with a comma like this, it means it's an OR. If either of these 3 conditions here is true, then the action for this case statement will be implemented. So, if the player chooses rock, the computer chooses scissors, or the player chooses paper and the computer chooses rock, or the player chooses scissors and the computer chooses paper, we declare the player as the winner. Otherwise, the computer wins the round. Once all rounds are completed, the game loop ends and the program prints game over to indicate the end of the game. Now, let's run the game. We see the message, let's play rock, paper, scissors. You have 3 rounds. Enter your choice, rock, paper, scissors. And I'm just going to choose rock. Computer chose paper. Computer wins this round. And you know what? I'm going to choose rock again. Computer chose paper. Computer wins this round. You know what? I'm stubborn. I'm going to choose rock again. Computer chose paper. Computer wins this round. Come on. All right, let's try it one more time. You know what? This time I'm going to choose paper. Computer chose rock. You win this round. I'm going to stick to paper. Computer chose scissors. Computer chose wins this round. Okay. I'm going to choose scissors. Computer chose rock. Computer wins this round. I'm going to go again. And I'm gonna choose rock. Computer chose rock, it's a tie. I'm gonna stick to rock. Computer chose paper, computer wins this round. Now for the tie break, I'm gonna choose scissors. Computer chose scissors, it's a tie, game over. Let me know in the comments, how did you try it and what would you do to improve this game? Arrays in Go are a fundamental data structure used to store a fixed size sequential collection of elements of the same type. In this example, we're defining a variable named bodyTypes. This variable is an array of size 3 and its elements are of type string. So this array will always contain 3 strings. From this, we can see that this is the syntax for declaring an array. The square brackets indicate that it's an array. The 3 indicates that it holds 3 elements, and the string indicates that the elements are of type string. So this array will always contain 3 strings. We can verify this by printing the array. In the output, we see that we have 3 empty strings. Highlighting with the mouse, 1, 2, 3. We can use the indexing syntax to assign the value of each element of the array. Body types index 0 equals sedan. Body types index 1 equals SUV. Body types index 2 equals convertible. And if we print the array, we can see that the array has these updated values. I'm gonna comment this out and show you another way to declare the array. Here, we're declaring the array and initializing it in one statement, which is handy when you have a small array like this one. Again, we can print the array to make sure we get the same outcome. And we do. Also, using the indexing syntax, we can access or get individual elements of the array. Here we print body types index 0, then body types index 1, and body type index 2. When we print this, we see the individual elements printed. A 2D array is essentially an array of arrays. It can be visualized as a grid or a table where you have rows and columns. Each element in a 2D array is accessed by 2 indices, one for the row and one for the column, i.e., one index for the outer array and the other for the inner array. In this code, we define a 2D array named car fleet. This array has 3 rows and 2 columns. Essentially, we're defining an array of size 3 where each element is an array of size 2 and each element of the inner array is a string. To assign the values, we are using the 2 syntaxes described earlier. First, we are using index 0 to assign the value of the row. This value is a new array of size 2 and we're initializing it with 2 strings. The first is 5 sedans available and the second is 2 sedans booked. These 2 strings represent 2 columns of the first row. Similarly, we're assigning the second row using index 1 and filling the columns with the status of SUVs. So these are the columns of the second row. And in the same way, we're assigning the third row using index 2 and filling the columns of this row with the status of convertibles. Then we print the whole array of arrays and we run the code. Sure enough, there are square brackets here and here to denote the outer array, and there are 3 inner arrays here, here, and here. In the first array, we can see the status of sedans. In the second array, the status of SUVs, and lastly, the status of the convertibles. Now let's try and format this output a little better. Let's first print a header here, car fleet status. To print each element, we first need to loop over each row. So let's create a for loop, and here's a tip for you. In VS Code, if you just type for and hit the tab key, you can see that it creates a skeleton for a for loop for us. We're happy with I for a variable name and we want to start with 0. So we just press tab again. It jumps to the condition. Here we just replace count with len car fleet, which means we want to iterate until the length of car fleet minus 1. The length of car fleet is 3 and we want to stop iterating at 2. We hit tab again. We're happy with incrementing I by 1 after each iteration, so we'll hit tab again. And we're brought to the body of the loop. As we've discussed, each element of this array is an array itself. Let's capture this array in a new variable. Let's call it row, and its value is gonna be carfleet index I. And just to confirm, let's hover over row here, and we see that it's defined as var row array of 2 of type string. And since this is an array, we need to create another for loop within the outer loop to iterate over items of the row. When you have a loop within a loop, this is called nesting. We nest the loop within a loop. The inner loop is called a nested loop. Using the same trick we just learned, let's type 4 and hit tab. This time we need to change the variable since we're already using I for the outer loop. So let's just use j and hit tab. This time the counter j is less than len of row because we want to iterate over the whole array. We hit tab and we increment j after each iteration. Within the loop's body, we use fmt.print to print the value of the column. We're not using println because we don't want to print each column in its own line. We want to print all columns in the same line, separated by a space. After the inner loop and within the outer loop, we use fmt.println without any arguments to print a new line. Let's run this program and see what the output looks like. We get 3 lines representing 3 rows, and in each row we get 2 columns, one with the number of cars available of a certain body type and another for booked cars of that body type. Slices in Go are a flexible and more powerful alternative to arrays. In this first example, we define a new slice using the syntax var fuel types square brackets string. Notice how similar is it to the declaration of an array. The only difference is the absence of a size. Now, we print the length of fuel types, and in the code, we get 0, which makes sense since the slice has no set size and no elements. And since it has no elements, the 0 value of the slice is nil. You can verify this by printing the slice is nil, colon, and pass fuel types double equals nil, which, as we discussed earlier, creates a new Boolean variable. If we run this code, we get the slice is nil true. This example demonstrates that slices are initialized to nil and have a starting capacity of 0. Next, let's look at this example. Here, we're declaring and initializing the slice in a single statement. Again, notice the similarity to the way we did this for the array, except we're not setting a size. When we run this, we get the slice printed. Now, let's add a new element to the slice. We do this by using the built-in function append. We pass the fuel types slice and the new element we want to add it. Append does not change the slice in place. Instead, it returns a new modified slice. And we can override the existing fuel types with the modified slice that is returned by append. Let's print the slice and run the program. Indeed, we get the updated slice with the new fuel type added. Furthermore, append accepts multiple items to add. So here, in addition to diesel, we can also add hydrogen. And if we run this, we see that hydrogen is added too. This example shows the flexibility in slices in that we can modify a slice dynamically and not just on initialization. Let's look at another example. This first line creates a slice of strings, fuel types, with an initial size of 3. Make is a built-in function and we can use it to initialize the slice with a predefined length. At this point, each element of the slice is set to the 0 value of its type, which is an empty string. To verify this, let's print the length of the slice, whether it is nil, and print the slice itself. Let's run this. We get 3 for the length. The slice is nil, false, and we get a slice with empty strings. So the make keyword, we can use it to create and initialize a slice with a predefined length. But that doesn't mean that we can't add additional elements to the slice. So unlike the array, we can add additional elements to the slice. And similar to arrays, we can set elements by indices. Set the first element to electric, the second to gasoline, and run the code. We see that the slice now contains electric, gasoline, and an empty string as the third element. Next, let's use the append function to add 3 new elements: hybrid, diesel, and hydrogen. Print the updated slice and run. This prints the updated slice, which now contains electric, gasoline, and an empty string: hybrid, diesel, and hydrogen. This highlights a very important aspect. The third element is initialized with an empty string and was never set. When we append to the slice, we add new elements, but not update the empty one. If we wanted to set the third element, we'd have to do this using index 2. I want to show you another built-in function, copy. Let's first create a new slice, fuel types copy, with the same length as fuel types using the make function. Then let's call copy, passing the destination slice first, then the source slice. Let's print the copy slice and run the program. Indeed, we see that the copy matches the original slice. Notice that copy modifies the destination slice in place, unlike append, which returns a new slice. In this tutorial, we'll look at the slicing syntax. This code snippet provides a demonstration of the slicing syntax in Go. Slicing is a powerful feature that allows you to create a new slice by selecting elements from an existing slice. Let's break down how it's used in this example. First, we create a fuel types slice and initialize it with gasoline, diesel, electric, hybrid, and hydrogen. Now say we want to create a new slice that creates the most popular fuel types. We can simply do this. Using the short variable declaration syntax, we declare popular equals fuel types open square bracket index 0 index 2. This statement creates a new slice popular from fuel types. It starts at index 0 inclusive and goes up but not to include index 2. So popular will contain the first two elements from fuel types, gasoline and diesel. Let's print the popular slice and run the program. Indeed, we get gasoline and diesel. By the way, 0 here is optional, so we can remove it and we'll get the same result. Now say we want to create a new slice to contain clean fuel types. We can create a new variable clean equals fuel types index 0 that's it. Since no index is specified, this includes all elements from 2 onwards. Let's print clean and run. Indeed, clean includes electric, hybrid, and hydrogen. A small exercise for you: create a new slice called electrical that contains electric and hybrid. Pause the video, try it out, and come back. We create electrical equals fuel types 0, 4. This slices fuel type from index 2 up to but not including index 4. Therefore, electrical includes elements electric and hybrid. Let's print it and run. Indeed, electrical includes electric and hybrid. Maps in Go are used for storing a collection of key value pairs. Maps are the equivalent of dictionaries and hashes in other programming languages. In this first example, we create a map named car inventory. The map keys are of type string and the values are of type int. Again here, notice the use of the built-in make function to create a map. So this is the syntax of declaring maps. We use the map keyword, then between the square brackets we specify the type of the key, and after that outside of the brackets we specify the type of the value. Both types can be anything. The key can be of any type. It doesn't just have to be a string. It can be an int, a float, or even a custom type. We will talk about those soon, I promise. The same thing for the value. It can be of any type. We populate the map with car types and their quantities using this syntax. Car inventory, between square brackets, we specify the key, in this case sedan, equals the value, in this case 25. We also add SUV 15 and convertible 10. Let's print this and run the code. We get car inventory map convertible colon 10 SUV colon 15 sedan colon 25. We can also create and initialize the map in one statement using this syntax. This directly initializes the map with key value pairs within the curly braces. Let's print this and run. We get the same result. We can use the len function on the map to get the number of key value pairs. If we run this, we get types of cars 3. In maps, values are accessed using their keys. Here, we're accessing the value associated with the key sedan. When we run this, we get 25 sedans, which is the value we assigned earlier. And if the key doesn't exist, we get the 0 value of the map's value type. So here we format print. We have placeholder, copays, and pass car inventory of the key copay. Run the code. We have 0 copays because the value of the map is of type int. We get the 0 value of type int, which is 0. We can update the value associated with the key after it has been initialized, like this. Here, we're updating the value associated with the key sedan to 20. And if we print updated inventory and run the code, we can see that the value associated with sedan is now 20. Maps are incredibly useful in situations where you need to maintain a collection of unordered elements and quickly access them using keys. Let's look at more examples. We start with the map we declared previously. Now say we no longer rent convertibles and we want to remove the entry from the map. We do this by using the built-in function delete to remove the key value pair with the key convertible. If we run the code, we can see that our map has convertible initially, but after the call to delete, there is no more convertible key. I want to show you how we can check if a key is present in a map. When retrieving a value from a map using a key, Go syntax not only returns the value associated with that key, but also a Boolean value indicating whether the key actually exists in the map. And we can use this Boolean in an if statement like this and print fmt.printf. We have placeholder convertibles, num convertibles. However, a better way to write this code block would be like this. This is an idiomatic Go pattern. This checks for key convertible in the map. If found OK is true, it prints the number of convertibles, otherwise it does nothing. This pattern uses the short variable declaration inside the if statement, which scopes variables num convertibles and OK to the block of the if statement. These variables can't be used outside of the if statement block. You'll see this pattern a lot in Go code, and most of the time the Boolean variable will be named OK. Even though it's not really required, you can name it anything, but in almost all cases you'll see it named OK. To clear all key value pairs from a map, we can use the built-in function clear. Run the code, we just get map and empty square brackets. We saw an earlier example on how to use a for loop to iterate over the 2D array. But a better way to loop over an array, a slice, or a map would be to use the for range loop. In this example, we utilize an array of strings named body types and set its elements to sedan, SUV, and convertible. The for range loop iterates over body types. For each iteration, it provides two values: the index I and the item body type. Then we print both the index and the item, and if we run this code, we get 3 lines with each line containing the index and a body type. If you only specify one variable in the loop, it captures the index of the array. If we run this, we get index 0, index 1, and index 2. If you're interested in the value but not the index, you'll have to specify two variables. But on the index, you can just use the blank identifier underscore. All these examples will work exactly the same for slices. So if I come here to body types and remove the size 3, turning it into a slice, and run the code, everything works the same. Now let's see how we can iterate over a map. Again, for maps, we use for range to iterate over a map. And just like with slices, we can expect two parameters to be returned by range. The first is the key in the map, and the second is the value. In this first loop, we're capturing the key in a variable body type, and we're capturing the value in a variable count. And then we just print body type and count. If we capture only one return from range, then that will be the key of the map. Here, we're capturing the key of the map in a variable body type, and we're printing. If you want to capture only one variable, and that variable is the value of the map, not the key, then we have no choice but to define two variables. However, the first one can be the blank identifier underscore. In this example, we're capturing the first return as the blank identifier and the second as a variable count. We declare an int variable total inventory and initializing it to 0, and within the loop, in each iteration, we add the count in each item of the map to the total inventory, and at the end, we just print the total number of cars. Alright, let's do an exercise. Let's write code that checks if a string is a palindrome. A palindrome is a word or other sequence of characters that reads the same forward and backward. Some examples of palindromes are kayak, radar, madam, and the phrase madam, I'm Adam. Feel free to pause the video and try it out yourself, then come back to see my solution. First, we declare a variable named input and assign it the value madam, I'm Adam. The input string needs to be normalized, which means removing non-lettered characters like spaces and punctuation and converting all letters to the same case, either upper or lower. The first step in normalizing the string is iterating through each character. The for range can be used to iterate over a string. However, each iteration variable isn't a string, rather it's a rune. We've already talked about runes in the strings tutorial before, but no harm in a recap. We mentioned that in Go, the concept of a character is called a rune, and that a rune is an integer that represents a Unicode code point. And just so we can visualize this, let's print R in the body of the loop and run the code. Each of these numbers is an integer representative of a character. So 77 represents capital M, 97 represents small a, 100 represents small d, and so on. Now back to the loop. To check if a rune represents a letter, we can use the function isLetter from the Unicode package. This function returns a boolean true or false if the supplied row is a letter. So we can do if unicode.isLetter, and within the if block, first convert the row back to a string using this conversion syntax, and let's convert the letter to lowercase. And lastly, append the letter to the normalized string. This completes the first step, and we now have a normalized string with only lowercase letters. The next step is to check if it's a palindrome. We first create a variable isPalindrome and initialize it to true, and we capture the length of the normalized string in a variable length. We create a for loop iterating from 0 up to half of the length of the normalized string, because we only need to iterate over the first half of the string. We need to compare characters from the start and end of the string, moving towards the center. So we need to compare the character at index 0 with the character at index length -1, and the character at index 1 with the character at index length -1 -1, and the character at index 2 with the character at index length -1 -2, and so on. This is easy to express in code like so. If normalized index I not equals normalized index length -1 minus I, then this isn't a palindrome. Set is palindrome to false and break out of the loop, since we don't need to compare anything else. If this condition is never satisfied, then this line will never execute and is palindrome will remain true. The last thing we need to do is just check if is palindrome and print it's a palindrome. Else, print it's not a palindrome. Let's run the code, and sure we get it's a palindrome, since we know this string is a palindrome. Let's change the input to kayak and run the code. Again, it's a palindrome. Now let's change the input to something like kayak is fun and run. We sure get it's not a palindrome. Okay, let's set it to 1 2 3 to 1. Sure enough, it's a palindrome. Let's set it to 1 2 3 1 1 and run. It's not a palindrome. A function in programming is a self-contained block of code that encapsulates a specific task or related group of tasks. At the beginning of the course, we created the main function. From this, we can see that functions in Go are declared using the func keyword, followed by the name of the function, followed by parentheses, then opening curly brace to mark the start of the body of the function, which is all the statements that make up the function, then a closing curly brace to mark the end of the function. We've also seen functions that accept input. Let's create a function that adds cars to the car inventory map we created in a previous tutorial. Let's type func add to inventory, then the parentheses, and inside the parentheses we can add any arguments the function expects. This function expects a car body type and a count. We first add body type, then we must inform the compiler what's the type of the parameter, just like with variables. In this case, string. Then comma, then we add the next argument, which is count, and its type is int. We only add commas between parameters, so since this is the last parameter, no commas needed. Then the curly braces. And I'm just gonna paste the function body here. In the first line, we're updating the count of a particular body type, and in the second, we print the description of the operation. And we can call this function from main like this. We just type the name of the function, add to inventory, then open parentheses, then we pass the arguments. For the first argument, we pass sedan, and for the second argument, we pass 10. Then we just print the updated inventory for visibility. Let's run this code. Sure, we get sedan added, new count 10, and in the second line, we get the updated inventory. We can go back to the main function and call add to inventory to add 7 SUVs and add 2 more sedans and print updated inventory. And let's rerun the program. Everything works as expected. As we've already seen many times in the course, functions can also return results. To return a result from a function, you must specify the return type in the function declaration. And the last statement in the function must be a return statement that returns a value of the declared type. In this example, getCount function is declared to return an int. And the last statement is a return statement that returns an integer value. Here's how we use it. Of course, we first call add to inventory to add the item. Then we call getCount directly from println. This will call the function and pass its return value to println. Functions can also return multiple values. You declare that by specifying the return types comma separated and between parentheses. In this example, getStatus function returns 2 strings. And by the way, the 2 return types don't have to be of the same type. In fact, most of the time they are of 2 distinct types. In this example, getStatus function returns 2 strings. We know this because there are 2 return types, string and string, separated by a comma. And the return statement returns 2 strings separated by a comma. This function returns a string for available cars and another for booked ones. Here's how we call it. After adding elements to the car fleet map using addToFleet function, we call getStatus, and on the left hand side of the assignment we declare 2 variables. We then print both of them. Let's run this and we get the expected output. The return parameters of a Go function can be given names and used as regular variables, just like the incoming parameters. This can make the code clearer, especially in case the function returns 2 or more parameters of the same type, like we saw with the getStatus function. So here we can edit the function like this. We can name this return type available and this one booked. And if we run the code, it still works just like before. Oh, by the way, these variable names don't have to match the return parameter names. We can rename these A and B and everything will work the same. Back at the function, we can now use available and booked just like normal parameters like this. Here we assign available to status index 0 and booked to status 1. We can now do return available, booked. Or we can just do a return without any parameter. If we run this code, it still works as before. I want to show you something really cool. You see how when we call println, we can pass as many parameters as we like? This is called a variadic function. And here's how it works. Here we're declaring a function sum that accepts any number of int parameters. And if we hover over numbers here, its type is a slice of int. So within the function, we can use a for loop to iterate over numbers just like any slice and just sum them up and return the total. You might be thinking, why not just use a slice as an argument? Well, if we do, then we'd have to always pass a slice. But when we declare it this way, using the spreading operator, then we can use it like this. Here we're calling it with 1, 2, 3, 4, 5. Here we're calling it with 700, 800, 900. And if we really want to call it with a slice, we can. We just have to use the spreading operator, like this. The spreading operator spreads the slice into its components. In Go, functions are first-class citizens. This means they can be treated like any other type. We can declare variables of a function type. You can pass a function as an argument to another function, and a function can return another function. As an example, here we have a function process number that accepts as an argument num of type int, and it accepts an argument operation. The type of operation is a function that accepts int as input and returns int as output. This means any function that accepts an integer argument and returns an integer result can be passed to process number as the operation argument. All process number does is call the operation function on the provided number and return the result. Here we have function double that accepts an integer, multiplies it by 2, and returns the result of the multiplication. We have another function half that accepts an integer, divides it by 2, and returns the result of the division. Both of these functions accept an integer argument and return an integer output, so they can both be passed to process number as an operation argument. We can try that here in main. First we call process number, pass 3, and pass the function double. Just the function name, nothing else, no need for parentheses, because we're not calling the function, we're rather passing it as an argument. And if we print the output of that, we get 6. Process number calls double with 3 and returns 6. Similarly, we can call process number and pass 16 and pass half as the operation argument. Running this, we get 8. We don't always have to pass a named function. We can also pass what's known as an anonymous function. Here, we're calling process number and passing 5 as the first argument, and for the second argument, we're passing an anonymous function. Anonymous because it doesn't have a name, it's just a body. The anonymous function is defined using the func keyword. It takes an input I of type int and returns a result of type int. Inside the curly braces, we can see the body of the function. All it does, it raises the input to the power 2 and returns the result. Of course, math.pow only accepts the float 64, so we cast I to float 64, and math.pow also returns a float 64, so we use int to cast the float 64 to integer and return it. And if we run this, we get 25, as expected. To see an example of how we use a function as a return parameter, let's look at closures. Let's say we have this function sequence that returns an integer. Within its body, it declares an int I, initializes it to 0, increments it by 1, and returns it. Now here in main, call this function a bunch of time, printing its return, and run the code. All we get is just 1 each time the function is called. This is no surprise, because each time the function is called, it declares I, which means it allocates a new memory location for it, and when the function ends, the garbage collector cleans up that memory location and the variable no longer exists. Now let's update the implementation of sequence so that it returns a function as output. Now sequence returns a function that returns an integer. Inside of sequence, instead of returning I, let's return a func that returns an integer. And in the body of that func, move the incrementing and returning of I. Pay attention to this syntax. Return func, parentheses, int, curly braces, a function body, then a curly brace. We're basically declaring a function that doesn't accept input arguments and returns an integer, and returning it as output by the outer function. Now to use sequence, we first declare a variable next int. The value of this variable is the output of sequence, and since the output of sequence is a function itself, we can call it with parentheses like this, and we can print its output. Let's repeat this a few more times and run. Now the output is 1, 2, 3, 4. This is because the returned function closes over the variable I, hence the name closure. Even after sequence has finished executing, the closure still captures and remembers the value of I. That is why every time it's called, it increments I, which it remembers its most recent value from the last execution. Now if I come here in main and create a new variable, new ints, and assign it the return value of sequence, and then call new ints as a function, guess what happens? the counter resets and we get 1. Because now this is a brand new call to sequence and new int is a new variable. And if I come here and call the old variable next int again and run, the old variable still remembers the previous value and we get 5. Now let's do a cool exercise with closures. Let's create the Fibonacci sequence. The Fibonacci sequence is a sequence in which each number is the sum of the two preceding ones. It starts with 0, then 1, then 1 again, since 1 plus 0 is 1, then 2, since 1 plus 1 is 2, then 3, since 1 plus 2 is 3, then 5, since 3 plus 2 is 5, then 8, then 13, then 21, 34, 55, 89, 144, etc. This is a very common interview question, so feel free to pause the video and try it out yourself, then come back for my solution. Also, I would love to know about what you tried and what was the outcome, so let me know in the comments. Now to the solution. We first declare a function named fib. This function takes no parameters. It returns another function which is a closure. This returned function takes no parameters and returns an int. Inside fib, two variables a and b are initialized to 0 and 1 respectively. These two variables are used to generate the Fibonacci sequence. The fib function returns an anonymous function, a closure. This closure captures its surrounding environment, specifically the variables a and b. Every time this closure is called, it calculates the next number in the Fibonacci sequence. The line a, b equals b, a plus b is a Go idiom for simultaneously updating a and b. A is assigned to the current value of b, and b is assigned to the sum of the current value of a and b. It returns the new value of a, which is the next number in the Fibonacci sequence. Initially, a is 0 and b is 1. When the closure is called for the first time, a becomes 1, which is b's old value, and b becomes 1, which is the sum of a and b's old values, which are 0 and 1. Each subsequent call updates a and b to the next values in the sequence and returns the current Fibonacci number. To use it and print the sequence, we just call fib and save its return value in a new variable f. Then we call f a bunch of times and print the result of these calls. Error handling is important because at some point a program will encounter an error. And if you don't handle the error properly, then will be met with unexpected behavior. Program can crash, or worse, the program can continue with an invalid state or corrupted data, just to name a few of very bad outcomes. Let's revisit our rock, paper, scissors game. I've moved all the code into its own function that will call from main. After running the code, I'm gonna enter rock with a small r. Computer chose rock, yet we still get computer is the winner. If we look at our code here, at the last switch statement, it defaults to computer 1. By default, string comparison is case sensitive. So even though the user thought he chose rock, in reality, he chose a different option. This is known as a logical error, and it leads to the program to continue with corrupted data. An easy fix for this would be to validate the user's input, like this. Here we're using the slices.contains method to check if the user's input is one of predefined choices. If not, we print a message informing the user that his choice is invalid and continue. Now if we run and I choose rock with a small r again, we get invalid input. However, a better way to handle this and an idiomatic way to handle this would be to ensure that the function returns an error in this case. Error handling in Go is distinct from any other programming language. Go handles errors by returning them as regular values. This is how it works. When the input is invalid, instead of printing a message, we return an error using the new function from the errors package. And we update the function to return an error type. And since the function now returns a value, the last statement must be a return statement. So in the last line of the function, we return nil. Now we call the function in main, we declare a variable error and assign it to the output of the function. We check if error is not nil, then just print the error. If we run the code and pass an invalid option, we get error invalid input and the program stops. If we pass legit values, the game continues to work normally. What we've seen here is the common idiom in Go for handling errors. A function explicitly returns an error as a value, and the caller checks if the function returned an error and acts accordingly. Naming the error value error is a common pattern as well. It's not required, we can name it anything we want, but this is the common way to do it. If the function returns a normal value, it should return an error alongside of it. The idiom here is to return all normal values first and lastly return the error. For example, revisiting our getCount function from earlier, we can update this function to return the count and an error. And at the start of the function, we can check if the provided body type is an empty string. If so, we return 0 for the count and an error. Otherwise, we return the count and we return nil for the error. It's good practice for functions to return an error value to handle error scenarios. In fact, most of the built-in functions we've used so far return an error as their last value. If the function executes successfully, the error is nil, otherwise, it is an error describing the problem. Here are a few examples. fmt.println that we've been using all along returns the number of bytes written and any errors encountered. strconv.parseBool that we've seen earlier returns the boolean value represented by the string or an error. If we hover over its documentation again, it says it accepts 1 t true 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 0 f false false false. Any other value returns an error. We'll be using errors a lot from this point on in the course, but here are a few best practices regarding handling errors. First, handle errors when they occur. Go encourages handling errors as soon as they arise, which leads to more robust code. Use meaningful error messages. Clear and descriptive messages can greatly aid in understanding and debugging errors. But perhaps the most important of those is avoiding ignoring errors. Earlier in the course, when we used strconv.parseBool, you saw me ignore the error by specifying the blank identifier underscore for the error returned by the function. This is a very bad practice and it's not encouraged. If you know a function returns an error, it's always better to define a variable for that error and check it. If it's nil, all good, the caller should continue, otherwise it should be dealt with then and there. The usual way to report an error to the caller is to return an error as an extra return value. But what if the error is unrecoverable? Sometimes the program simply cannot continue. For this purpose, there is a built-in function, panic. Panic in effect creates a runtime error that will stop the program. To see an example of that, we can go back to our game of rock, paper, scissors and update it so that we can call panic instead of returning an error. If we run this code and pass rock with a small r, we get panic, runtime error, invalid input. However, I only use panic here just to show you, but this isn't a good use case for panic. A panic should use sparingly and only in situations where the program can't continue to run safely. An example of that would be if, for example, you have a REST API that requires specific configuration. If that configuration is missing, there is no way for the API to run. In that case, it might be good to use a panic. We use structs to define a new type. So far, we've looked at basic types in Go like strings, integers, floats, and booleans. We've also looked at composite types like arrays, slices, and maps. While these are very useful, as we've seen, many times they want to model more complex concepts. For example, say we want to model a bank account. A bank account has attributes like account number and balance. For that, we can define a struct like this. This first line is saying we'll define a new type using the type keyword. Its name is bank account and it's a struct. Between the curly braces on the following lines, we define the structs fields. Each field has a name and a type. The field account number is of type string and the field balance is of type float64. From this, we can see that a struct in Go is a composite data type that groups together variables under a single name. These variables within a struct are called fields. To create an instance of a struct, you can declare an instance of that struct type and initialize its fields like this: var account bank account, just like creating any other variable. Then, using variable name dot field equals, we can set the field values like this. If a struct is declared without explicit initialization, its fields are assigned the zero values of their respective types. We can see this here by printing the value before initializing the fields. If we run this, we get an empty string for name and 0 for balance. Alternatively, you can use this shorthand notation, which is the most commonly used way. Notice here we use a colon for assigning values to the fields rather than the equal sign. We can also access individual fields of a struct like this using the dot notation, variable dot field. You can also use pointers to structs. This is very common and is useful for passing structs to functions without copying them, as we will see soon. A struct can embed another struct like this. Here we define a new struct, audit info. It holds creation and last updated timestamps. We then modify bank account struct to embed audit info struct, which means the bank account struct now contains all the fields of audit info. And we can create a bank account instance like this. For the audit info, we just create a new audit info instance as part of the initialization. We can then access audit info fields from the account instance directly, like this. The time package provides functionality about date and time. Time.now returns the current date and time. You can define functions on a struct. A function that is defined on a struct is called a method. Display balance is a method defined on bank account struct. We define a method on a struct by adding an argument of the struct type using this syntax. This argument is called a receiver. You call display balance like this. Notice that the account variable does not need to be passed to display balance function. It automatically receives it, hence the name receiver. And if you attempt to call display balance in a standalone fashion like this and pass account, we get an error. Display balance undefined, because display balance does not exist independently of its containing struct. Let's look at another method. Deposit is a method used to add funds to an account. Two things should stand out about this method. Firstly, notice the amount parameter is defined after the method's name, just like you normally would with any other function. It is not passed the same way as the receiver. In fact, a method can only have one receiver. The second thing is that the receiver is a pointer. In the case of display balance, it is called a value receiver. But in the case of deposit here, it is called a pointer receiver. Understanding the difference between these two is extremely important because it affects how methods interact with the struct's data. When a method is called on a struct with a value receiver, it receives a copy of the struct. Any modifications made within the method are made to the copy, not the original struct. Therefore, these changes are not visible outside of the method. Let me explain using an example. Let's temporarily change the deposit method to receive a value rather than a pointer receiver. In main, let's print balance before deposit here and print balance after the call to deposit. When we run this, we get balance before deposit 1000 and balance after deposit 1000, which is obviously not the behavior we want. Before I explain why it behaves like this, let me change deposit back to receive a pointer instead and run the code. Now we see that the balance is updated to 2000 correctly. That's because with the value receiver, when we call deposit, Go automatically creates a copy of the account instance and passes it to the deposit method. Deposit updates the balance on that copy, and when the method exits, that copy is garbage collected. Changes to it no longer exist. So the original account instance remains exactly the same. Its balance does not get increased. And to show you that this is the case, let's change the receiver on deposit back to be a value, and inside of deposit, let's print the value of balance. When we run the code, we see balance before deposit 1000, balance inside of deposit function 2000, and then outside the function we see balance after deposit 1000 again. On the other hand, with the pointer receiver, deposit method receives a reference to the account instance. And when the function updates the balance, it updates it on the original account instead. And this change is visible outside of the method as we've seen. If you're still unclear about this, I highly suggest you go back to the lesson about pointers from the beginning of the course, and you can come back and rewatch this lesson again and again. And if you have any questions, don't hesitate to leave them in the comments. Now, a fair question would be when to use a value receiver and when to use a pointer receiver. Value receivers are typically used when the method does not need to modify the original struct. For example, the display balance method doesn't need to modify the original bank account, so a value receiver is okay. If the struct is small and copying it is efficient. You see, copying a struct means allocating additional memory for the copy, which could be an issue for large structs on performance critical applications. The third reason is you want to ensure the method does not inadvertently modify the struct's data, thus maintaining immutability. On the other hand, pointer receivers are used when the method needs to modify the original struct, like deposit method we've just seen, or the struct is large and copying it could be inefficient. In summary, if the method needs to change the struct state or the struct is too large, use a pointer receiver. If the method only reads from the struct or the struct is small and easily copied, use a value receiver. If you're still unsure, unless you're working with a performance critical application, you don't need to overthink this and just go with a pointer receiver. Let's test our understanding with an exercise. I want you to create a method withdraw on the bank account struct that accepts a float parameter and checks if there is enough balance in the account. If there is, it subtracts the amount from the balance. Pause the video, try to write this or think about it, and then come back for my solution. We'll create a method withdraw that has a pointer receiver since we want to ensure that changes persist on the instance. It has an argument amount of type float64 and it returns an error. The function first checks if the count.balance is less than the requested amount. If so, we return an error saying no sufficient funds. Otherwise, we subtract the amount from the balance and return nil. Now let's look at more struct features by extending this solution to become a simple banking solution. Here we're creating a customer struct with the fields name of type string and accounts of type slice of bank account, since a banking customer can have multiple accounts. Customer defines add account method which accepts a bank account argument and appends the new account to the customer's accounts. This is an example on how a method might accept arguments that are typed as different structs. It also defines display accounts. Here notice the value receiver, since this is a displaying method and it doesn't make any changes to the struct. The method loops through the customer's accounts and calls display balance on each of them. We then have a bank struct with a name field of type string and customers field that is a type slice of customer. Add customer method is defined on the bank to append the customer to its customer's slice. And display customers method loops through customers and calls display account on each of them. And here's how everything ties together. Go doesn't have a concept of a constructor like some other languages. Instead, we need to create constructor functions. The idiom is for the function to be called new followed by the name of the struct, and it either returns the struct itself or a pointer to it. So for the bank struct, we create a constructor function new bank that accepts a name argument and returns a bank pointer. Similarly, we create new customer and new bank account. Now we can go back to main here and replace each struct initialization to a call to its constructor function. Now customer.addAccount is complaining because it expects an account value, but we're passing a reference. We can easily fix this by dereferencing the account with an asterisk. And we can do the same for add customer. We've seen how structs allow us to model complex concepts that can't easily be modeled with built-in types. But what if there's a built-in type that can model our concept and we just want to extend to the functionality of that type? Here's an example. A bank account number is a string, but it is bound by certain restrictions. It needs to be a certain length, or it might need to start with a certain number. Go allows us to create a type declaration, like this. Type account number string. Here we're declaring a new type called account number and its underlying type is string. This is a completely different type. In fact, we can now declare new variables of type account number like this. And just to show you it's a different type, you can print the variable's type. And as a sanity check, create a new variable of type string and print its type. It tells us that ACCT is main.account number. Account2 is string because account number is defined in the main package. We can now define methods on account number like we would on a struct. Here we declare is valid method which checks if the account number is exactly 10 characters long. Notice here that before we can pass a to the length function, we had to explicitly convert it to a string. That is because even though it is based on string, it is not a string. We can now update our bank account struct to use the new type for the account numbers field. Let's create an account instance, and if we print account.accountNumber.isValid, we get false. If we update the declaration to include a 10th character for the account number here and rerun the code, we now get true. Notice how we still assign a string to account number. Even though it is not technically a string, Go does the conversion automatically. Another form of a type declaration is creating a type alias. Here, Palace is an alias to float. Notice the subtle difference in declaration. Here with an alias, we use the equal sign before the type name. Balance and float are now interchangeable. So if we declare a variable balance of type balance and print its type, we get balance is float64. This is extremely powerful and useful, and you will see it used a lot in Go code because it simplifies the code and it makes it more readable. If you want to simplify a complex type or you want to declare your own meaningful type, you can use a type alias. And if you want to extend the functionality of an existing type, you use a type declaration. And you're going to see more of those when we do our project. In Go, an interface is a type that specifies a set of method signatures, i.e. behaviors, without implementing them. Any type that implements all those methods is said to implicitly satisfy the interface. Consider the interface io.reader from the io package. This interface has a method read that accepts a byte slice as input and returns an integer type and an error type. Now consider our struct here, XML reader. XML reader has a field data of type string and it defines a method read with the same signature as that of io.reader. Method read accepts a byte slice as input and returns an int and an error. Because of this, XML reader satisfies the io.reader interface. Next, take a look at the function readConfig. ReadConfig accepts an input of type io.reader. And because XML reader struct satisfies the io.reader interface, we can pass an instance of XML reader to readConfig, as we do here in main. We create an instance of XML reader, then we can pass it to the readConfig function. Okay, let's step back a little and ask the question, what's the use of interfaces? I'm going to use an analogy to explain interfaces. Imagine an electric appliance. It could be anything like a TV, a toaster, or washing machine, whatever. Despite their different functions, they all share one common requirement. They need to be plugged into an electrical power source to work. Each appliance comes with a plug designed to fit into the power socket. Whether it's a TV or a toaster, as long as the plug fits the socket, it can receive power. Translating this back to Go, the power socket is like Go interfaces. It defines expected behavior, like the shape and size of the electrical plug, but doesn't concern itself with the specifics of what the appliance does. The implementer appliance plug represents types in Go that implement the interface. Like different appliances, they perform different functions but share a common method of interaction. When you write a function in Go that accepts an interface type, it's like creating a power outlet in your house. Any type or appliance that implements the interface that has the right plug can be used with this function. I want to show you another interface that we've actually been using all along. The error type. As you can see here, type error is an interface that defines a method error that returns a string. In Go, an error is any type that implements the error method. This simplicity means that you can create custom error types by implementing this interface, which can be very useful for providing more error information. Let's look at this example. API error is a custom error type with the additional message and code fields. API error defines a method error that returns a string. Now take a look at makeRequest function. It is declared to return an error type. It returns an instance of API error because it satisfies the error interface. Call the function in main, capture the returned error and print it. And when we run the code, we get code 404 not found. The empty interface, denoted by interface followed by opening and closing bracket, plays a significant role in Go due to its ability to represent any type. Any type satisfies the empty interface, whether this is a built-in type like int or string, or a user-defined struct, or even a slice. It's common to see functions that accept the empty interface as parameter when the function needs to operate on data of unknown or varying types. In this simple example, doSomething function accepts a v parameter of type empty interface. It then just prints it. In main, we're first calling doSomething with the string hello. We're then calling it with the integer 1, 2, 3, and later calling it with the float 4.5. If I run this code, I see hello, 1, 2, 3, and 4.5 printed. Another closely related concept to the empty interface is the type assertion. Type assertion allows us to assert if an empty interface is a specific type. Looking at this example, we're defining a variable I as an empty interface and assigning it the string hello. Next, using this syntax, I dot in between parentheses string, we're asserting that I is a string and assigning the value to s. So if I hover over s here, I see that s is a string. A better form of assertion though is specifying two variables on the left hand side of the assignment. In this example, s and OK. S is the string and OK is the boolean that specifies if the operation succeeded or not. This is better because it's safer. If the assertion is successful, then OK will be true and S will contain the value. If the assertion is not successful, OK will be false and S will contain an empty string. And as you can see from this line, we're declaring F as float 64 and again OK. And we're asserting that I is a float 64. And then we're just printing if and OK. Let me just run this code. In the first case, we say hello, which is coming from this type assertion. And then we're getting hello and true from this type assertion. Notice in the third case, we're getting 0, which is the 0 value for a float 64, and we're getting false. If we didn't specify OK for the type assertion and we went ahead and specified if only, this code will cause a panic. That's why it's always safer to specify two variables, one to hold the value and one to hold the success or failure of the assertion. I'm just gonna uncomment the code and run. I get a panic. This code shows the type switch. Basically, we have this do function that accepts an empty interface. Then using this syntax, we write different cases for the type of I. Do will inspect the incoming I. If I is an int, this line will execute and we'll get twice v is v multiplied by 2. If it's a string, we print the string is len characters long. And just like the normal switch, we have a default statement to fall back to whenever the other cases don't apply. And if I run this code with 21, I get twice 21 is 42. With hello, I get hello is 5 characters long. And if I pass true, I get I don't know about type bool. I'm gonna be using interfaces again in the next major project, and that should help you understand their usage further. So make sure to stick around for that. Generics have been a part of Go since version 1.18. They allow us to write functions and types that are abstracted over the types of their arguments and return values. This means we can write more general and reusable code. To really drive the point, I'm going to show you this example. Here we have a variable body types of type slice of string. Now suppose we want to remove the convertible from this slice. Before generics, this is how we used to do it. You would need to append two slices. The first slice starts from the beginning of the original slice up to the index of the element to remove. And the second slice starts from the element after the index of the element to remove until the end. So in this case, we're appending two slices. The first contains sedan and SUV, and the second contains hatchback and coupe, skipping convertible. And we assign the output of this operation to the original body type slice. And if I run this code, indeed I can see that convertible is deleted. Well, a fair question would be, how do we even get the index of the item to remove? Well, this can be easily achieved using a function like this. Here, find index accepts a slice of string and a string value. It loops through the slice and compares each value of the loop iteration to the incoming value. If there's a match, it returns the index. If there isn't a match, it returns -1. So now, instead of hard coding 2, we just call find index passing body types and convertible. And if I run this code, of course it still works. However, you can see how inflexible this is. This function works with a slice of string, but for a slice of int, you would need a new function. For a slice of floats, you need a different function. For a slice of struct types, you would need a unique function for each type. You could write a function with an empty interface, as we've just seen, and then use a type switch with type assertion. But that's still inflexible and error prone. Now, thanks to generics, we don't need any of this. We can use the function slices.deleteFunc from the slices package. This function accepts the slice we want to delete from, and the second parameter is a function to be used to decide the item to delete. Slices.deleteFunc invoke this function on each element of the slice, and all the elements that cause the function to return true are deleted. So now here we're calling slices.deleteFunc, passing body types, and for the second argument we're passing an anonymous function. If you need the reflection on anonymous functions and passing functions are arguments, you can go back to the lesson on functions. So what happens here is that the deleteFunc function loops through body types, and only body types that are equal to convertible will return true, and only those will be deleted. And if I run this code, indeed, we see that converter is being deleted. Slices.deleteFunc is a generic function that would work the same way with a slice of any type. Here, I have a struct type bank account, and in main, I have a variable account that is a slice of bank. We're initializing it with 3 instances of bank and then printing the slice before deletion. Then using deleteFunc, we're passing accounts, and again, we're passing an anonymous function. This anonymous function returns true if the bank account number is equal to 789. And if I run this code, I see the slice before deletion containing all 3 accounts and after deletion containing only 2 accounts. Let's define funcPrint. The argument to this function is a slice of t. Right away we see the compiler error saying t is undefined. That's because up until this point, this is a regular function. To make it generic, we need to tell the Go compiler that t is a generic type. We do that using square brackets between the function name and the function's arguments. Inside the square brackets, we need to tell Go what this t is restricted to. And here we're saying t any. That means t can be anything. Any is just an alias for the empty interface. And because any type in Go implements the empty interface, this function will work with a slice of anything. You can create stricter restrictions if you like. For example, you can say t error, in which case all the types implementing the error interface can be used with this function. You can even say t string, but then it defeats the purpose of a generic, so I'll stick with any. Inside the function body, we have a good old for range loop. It loops over the values and prints them. And the compiler is happy with this because even though it's a slice of a generic type, it's a slice nonetheless. Now we can use this function with bank accounts. We can use it with a slice of string, slice of int. It works the same every time. Now let's see the implementation of deleteFunc from the standard library. The function is declared to accept 2 arguments. The first is s of generic type s, and the second is a function del that is a func that accepts an argument of generic type e and returns a boolean. DeleteFunc returns a value of type s. Looking at the type restriction, e is any type and s is a slice of the same type. As we've seen with the previous car body types example, e was a string and s was a slice of string. And in the case of the bank accounts example, s with a slice of bank accounts and e was the bank account. The tilde symbol means that s can be both a slice of e and any type derived from the slice of e. This means if we declare a new type, car body type, that is derived from slice of strings, like we see here, we can still use it with deleteFunc even though car body types is not a slice, but it is derived from a slice. If the function didn't have this tilde, this code wouldn't work. It would only work with a slice. Now looking at the function body, it starts with a normal for loop that ranges over the slice s. I is the index and e is the value at each iteration. The line if del of v, this line invokes the past function del using the current element v to check if it should be deleted. If del returns true for the current item, meaning that it should be deleted, then the next logic is executed to delete the item. If not, we skip to the next iteration of the loop. The line j equals I initializes a new index j with the value of I. This index j will track the position in the slice where we need to copy elements that are not being deleted. The second for loop, this inner loop continues from the next element in the slice and goes through the rest of the elements. V equals s of I updates v to be the current element in the slice. The line if not del v checks if the current element should not be deleted. If so, this element is copied to the position at index j. Next, we just increment j by 1 to move to the next position in the slice. Once the inner loop finishes, the line return colon j returns the slice up to index j, which effectively cuts off any elements that were marked for deletion. If no elements were marked for deletion, that is, if del v condition was never true, the last line in the function return s is executed, basically returning the same slice. This logic is pretty much the same as the slice and append logic we used initially. It is just written differently so that it can be generic. Generics are not only limited to functions. We can declare a generic type as well, like the generic pair type here. Pair is a generic struct that holds a key and a value of any type. We then define a generic method describe on the pair struct. Method describe formats the pair as a string. Notice that the receiver of this method is the pair of kv, not just pair. Then in main, you can see that this is how we declare and use generic types. First, we create a variable int and string pair like this. Pair, int, string, then key is 1 and value string. Then we invoke the describe method on the pair. In the next example, we create a variable string and float pair, key is pi and value is 3.14159. Generics in Go are a powerful tool to allow for greater code reusability, because we can write functions and data structures that works with any type. They also offer better type safety, because unlike the empty interface and runtime type assertions, generics provide compile time type safety, which also means better performance. So far in the course, we've been working with fragments of code and they were all in the main.go file. However, in almost all real-world applications, you'll have loads of code composed of various types, variables, constants, functions, doing specialized tasks. Obviously, lumping all this code in one file is neither productive nor maintainable. In Go, code organization is centered around packages. A package is a collection of Go source files in the same directory that are compiled together. Let's clarify this with an example. Let's take all the code we wrote in the Structs lesson and move it into its own package. And let's name it BNK, short for banking. Go creators recommend that package names be lowercase, short, concise, and evocative. And we've seen that in standard library packages like fmt, strconv, and strings. I will start by adding a file to hold the bank account struct and its methods. I will name it bank_account.go. The first line of any Go file must be a declaration of which package it belongs to. So let's type package bnk, bank. Next, we need to declare the packages our file depends on. However, we rarely need to do this manually, because as you've seen from previous tutorials, all we have to do is use the package and VS Code adds it to the set of imports automatically. Next, we go ahead and declare any types, functions, variables, or constants belonging to the file. I will first paste the audit info struct definition, then the account number type declaration, then the struct, then the methods, and finally the constructor function. I will do the same for bank and customer. And now that we moved all the code to a new package, it's time to see how we use it from the main func, because that's the entry point of the program. Here in main, to declare a bank instance, I'll do bank colon equals bank dot, and you can already see IntelliSense suggestions. As soon as I choose new bank and hit enter, we can see the bank package imported automatically. I'll pass GoBank for the name. We've already seen the rest of the code, so I'll just paste the rest and run the code to get a similar result to what we got before. Now, going back to our package, there are very important points here. The first is that within a package, all members are accessible to each other. That's why even though audit info is defined in bank underscore account.go file, we were able to access it from other files. As far as the package is concerned, this file organization is for our own sake. From its perspective, all members live under one umbrella, the package. Also, I hope you notice that now the first letter of each struct field is lowercase, unlike before. The impact of that is that the fields become private. That means they can be accessed within the package but not outside of it. So if we go to main.go and try to fmt.println bank.name, we get an error that name is undefined. Let's actually right click on the name field and choose rename symbol, update it to use capital N. Now if we come to main and change this to use capital N, the error disappears. This is how Go achieves encapsulation. If something starts with a capital letter, it is exported, i.e. accessible outside of the package. Otherwise, it is only accessible within the package. Whether it's a struct, a method, a function, an interface, a variable, or a constant. So far in the course, we've only been using packages from the standard library, which is enough in many cases. But sometimes you may want to use functionality from a third-party library, which I'll show you how to do in this tutorial. But first, let me show you how a package is distributed for use by others. Let's open a new VS Code window here. Command O to open a folder. The folder doesn't exist as of yet. Let's click New Folder and I'll name it Bank and click Open. Let's open a terminal window and let's run the command go mod init pass a module path. A module path is a web location, usually a URL for a GitHub repo, where people will be able to find our modules and import it to use it in their own code bases. So I'll pass github.com/codebuilds-dev/bank. This is the URL for the GitHub repository where this code will live. Now on the left hand side, we see a go.mod file created. When we open this file, we see that it has the declaration module followed by the module full path github.com/codebuilds-dev/bank and the word go followed by 1.21.5, which is the version of Go installed on this computer at the time of the recording. Now let's copy the files from bank package in our original solution and paste them here. That's all the code changes I need. I just need to commit the changes to GitHub. So I'll do git add dot, then git commit -m, and for the message I'll just say add bank module. Now we just need to version our module, and we do that with a git tag. So I'll do git tag v1.0.0. Now I just push the code to GitHub and that's it. The module is publicly available for anyone to import and use. Now that our module is published publicly, we can import the bank package from it. Open the command line and run the command go get github.com/codebuilds-dev/bank. Now if we go check our go.mod file, we notice that there is a new require statement followed by our module full path and version. Go get also automatically creates or updates a go.sum file. This is used for checksums to ensure the integrity of the modules. We don't need to manage or modify these files manually. To use the package in the code, we just go to our main.go file, remove the old package import, and just hit Ctrl S to save again. We see the new package imported from GitHub. So far in the course, we've seen the commands go mod, go run, and go get. In this tutorial, I want to spend some time on some other Go commands. If we just run the command go, we get Go is a tool for managing Go source code. On the next line, we see usage, which explains to us how to use the command go command arguments. It then lists all possible commands with a brief description of each. And here we can see the ones we became familiar with: mod, run, and get, among many others. I won't go through all of them, but I will mention a few commonly used ones. The command build is used to compile the source code files and all dependencies. Dependencies are packages that we import using the import statement. And if the package contains a main function, it creates an executable binary for us. If you are on Windows, the executable will end in the .exe file extension. To use the command, we just run go build dot. Dot here means build the files in the current directory. This creates an executable that has the same name as the directory it was run from. If you wanted a different name, we could have passed it via the O flag like this. I'm happy with the name though, so I'll just pass it. We can now execute this executable by opening the file system and double click on the file. This runs the program and produces the output we saw earlier. And since this is an executable binary, we can share this file and redistribute it, and it will run even in environments where Go is not installed. If the package does not contain a main function, like the bunc package, then build simply compiles the package. This is usually used to check for compilation errors. The command install is similar to go build, except we pass a module path to it like we do with go get. It then downloads the code, compiles it to produce an executable, and places that executable in the bin directory of the workspace so it can easily be accessed and run. And we've actually used the install command at the beginning of the course when we install the Go tools. Let me show you that again. Just like before, we go to View, Command Palette, and search for Tools. Then select Go install/update tools. Now, if we look at the output window in Visual Studio Code, the second line says installing 7 tools at, and it shows the bin directory I just mentioned. And if I scroll down, we can see that installing some URL, then the location within the bin directory where the tool is installed. This is just the UI that shows you the result of running the go install command. The command godoc prints the documentation of a specified package. For example, if we type godoc fmt, we get the documentation of the fmt package. This is the same documentation we see online. If we just type godoc without a package name, we get the documentation of our own package. Our package has no documentation yet, but we will add it very shortly. You can get help information about any Go command by using the command go help, then passing the name of the command we want to get help about. For example, if we run the command go help mod, we get information about what is the command mod, what does it do, and how to use it. And we can use go help with subcommands as well. So we can do go help mod init. That gives information about the init subcommand of the mod command. Documentation is a good practice, especially if you're going to publish something for the public to use. As you've seen so far in the course, we often refer to the docs to learn more about how something functions and behaves. There are some established best practices and patterns for this. Here's an overview. Start with a comment immediately preceding the package statement. This comment is for the entire package and should provide an overview of its purpose and contents. If the package documentation is so long, it can be separated in its own file, like this. Document each exported, i.e. public function, method, type, constant, variable, whatever. These comments should be declarative and start with the identifier name. Be clear and concise. The first sentence should be a summary that stands on its own. Although Godoc does not support full markdown, it interprets line breaks and indented text as pre-formatted text, which can be used for examples or multi-line explanations. Group related constants, variables, types, and functions together to improve readability. And we've seen this in the bank package. We group types related to the bank account in the bank_account file, and types related to bank in the bank.go file, and types related to customer in the customer.go file. Be consistent in formatting and style. This includes capitalization, punctuation, and sentence structure. Now, taking all these recommendations and applying them to the bank package, here's the result. Alright, we made it to our first major project. I'm really excited to share this with you. This is the program that I built for my own personal use to assist me in picking stocks to trade. Along the way, you'll learn a ton of new things like concurrent programming, building an HTTP client to call a REST API, reading from and writing to a file, building command line interface, and more. Some background. I used a stock trading strategy called the OPG strategy, short for Open Price Gap. Very basically, this strategy involves trading stocks based on the gap in price from the previous day's close price to the current day's open price. Now, the key to this strategy is speed. The stock market opens at 9 a.m. and by 9:10 a.m. I should be done with my analysis and decided on which stocks to trade. A huge part of my analysis is news. In this short period, I need to review news about many stocks to help me decide. I had a real need for automation. So here are the program requirements. Load a bunch of stocks from a CSV file. Filter out stocks that aren't worth the trouble based on some criteria. For each stock, calculate the position. For each stock, fetch the latest news about the stock. Output the result of the analysis in JSON format. Let's fire up VS Code and open a folder. It doesn't exist, so I'll create it and name it OPG-analysis. And let's open it in VS Code. Next, I'll open the terminal and initialize our module by go mod init github.com/codebuilds-dev/opg analysis. Our go.mod file is created, so let's create our main file main.go. I will first build the whole application using all the functions and then refactor it to follow architectural patterns of real-world applications using interfaces, structs, and methods spanning multiple packages. Our first requirement is to load data from CSV file. I used to get my candidate stocks from an online screener in a CSV file that looks like this. It has 3 columns: ticker, which is the stock's ticker or symbol; gap, which is the price gap as a percentage of yesterday's closing price; and third, I have today's opening price. Before the program can read data from a file, it has to open it. We'll use the open function from package OS like this: os.open. This function accepts one argument, the file path. So let's for now pass ./opg.csv. This means the file is in the same directory the program is run from, and its name is opg.csv. This function returns an os.file type and an error type that describes any issues opening the file. Following good practice, we first check if the error is not nil, in which case we print the error and return. Otherwise, we'll continue to read the content of the file. Package OS provides a platform-independent interface to operating system functionality. The OS interface is intended to be uniform across all operating systems. So, os.open will handle the internal differences between different operating systems. The Go standard library provides the package encoding/CSV for reading and writing to CSV files. We start by declaring a variable r equals csv.newReader and pass the file variable f. NewReader returns a pointer to csv.reader. We then use r.readAll to read the content of the file. ReadAll returns the rows and columns in slice of slices of string, where each element of the outer slice represents a row, and each element of the inner slice represents a column value in that row. ReadAll also returns an error type that describes any issue reading the file. Just like before, we first check if error is not equal to nil. We print the error and return. The first row in the file is a header, so we'll delete it using slices.delete. We pass rows 0 and 1. That means delete one row starting at index 0. Then we loop over the remaining rows. We create a for loop to loop over rows. Since rows is a slice of slices, the variable row is a slice. We know that the first column contains the ticker, The second column contains the gap, and the third column contains the opening price. So using the indexing syntax, we can get these values from the row. Ticker is row of 0, gap is row of 1, and opening price is row of 2. At this point, we need a type to group these values. So let's create a struct, stock. It has the field ticker of type string, gap float64, and opening price float64. Back at the function, let's declare var structs slice of stock before we enter the loop. And inside the loop, on each iteration, let's append to the stock slice a new stock. Right away, we get those errors on gap and opening price, because these are of type float64 and our variables are of type string. So let's fix this by instead calling strconv.parseFloat, and we pass row of 1. This of course returns an error if the conversion fails. And if there's an error in one row, we don't want to abandon the whole operation. We just want to exclude that one row. So I'll use continue to skip to the next row. I'll do the same for row of 2. Now the error is gone because gap and opening price are now of type float64. So now we have all of the data from the CSV file in a slice of stock objects. Let's actually remove this code from main and into its own function. Let's call it load. Load returns a slice of stock and an error. And instead of the hard-coded file path, let's pass it as an argument path. And let's fix the code here to return nil and the error. And here as well. And if all is well, we return the stocks and nil for the error here at the end. There's one thing left to do, and that is closing the file. To do that, we call the close method on the file, like so, f.close. However, this isn't the best way to do this, because imagine the function returns before we reach this point, for example due to an error here or here. We could call f.close at these points before returning, but that's inefficient and error prone. For this, Go provides the defer keyword. Immediately after we successfully open the file, we use defer f.close. The defer keyword ensures that f.close is always called before the function ends, whether due to an error or otherwise. So we'll always have that peace of mind. This also improves the code readability by saving us from having to call f.close in multiple places. We can now call load from main and pass the file path. We capture the returns in variables stocks and error, and check if error is not equal to nil. We print the error and return from main, effectively terminating the program. This completes the first requirement, and next we need to filter out the unworthy threads. My CSV file would typically include tens of entries, but only a handful are worth further analysis. For simplicity, the only criteria I'll implement here is if the gap is greater than or equal 10%. So let's come up here and filter out the stocks by removing the ones where the gap is less than 10%. I'll do this using the delete function from the slices package. I'll pass stocks, and for the second parameter, I'll pass an anonymous function. Inside the function, I will just check if math.apps of s.gap is less than 0.1, return true, else return false. What this means is run this anonymous function on each element in the slice, and any element for which the function returns true, delete it. Of course, I'm using math.apps because the gap can be both negative or positive. Positive if today's price is more than yesterday's closing price, and negative otherwise. And we can simplify this if statement like this. Return math.apps of s.gap less than 0.1. And that's it for the second requirement. The next requirement is calculating the position. The position is 4 things: the price at which to buy or sell, how many shares, the price at which to exit and take my profit, and the price at which to stop my loss if the stock doesn't go my way. I created the struct position to model this concept. I won't bore you with the details about how I calculate these numbers. I only ask you to pay attention to these variables here. Account balance, loss tolerance, max loss per trade, profit percentage. I'm just hard coding these values here for now. The function calculate accepts as arguments the gap percentage and the opening price of a stock. It calculates the position and returns it as a position instance. As I said, I won't go into details of the calculations, but if you're curious, feel free to pause the video and read the code. Back in main, I'm gonna loop over stocks using a for range loop, and in each iteration, I'll call calculate, passing stock.gap and stock.opening price. I'll capture the result in a variable position. At this point, I have an instance of the stock struct and an instance of the position struct, and I need to combine those two. So I'll create a new struct to combine them. I'll call it selection, which will represent a selected stock. Selection will form my basis for trading decision making. So it will contain the ticker and it will embed the position. So back at the loop, I'll create an instance of selection. The value of ticker will be stock.ticker and position will be the position variable. Outside of the loop, I'll create a slice of selections, and back inside of the loop, I will append this selection to the slice. Next in our requirements list is to fetch the latest news about each stock selection. I'm going to be using a site named Seeking Alpha, which is a great source of stock news. It has a REST API that we can call for a specific stock, and it will return all news articles about the stock. To try this out, I'm going to be using a tool called Postman that you can download from this URL. I will create a new GET request and paste the URL. For the ticker, I'm passing AAPL, and I'm limiting the results to 5. To authenticate with the API, I'm going to head over to Headers tab and add the header x-rapid API-key, and I will paste my API key. When I hit send, takes a couple of seconds and it returns the JSON output. We can scroll through this result here to see things like published on, the title, comment count, etc. For my trading strategy, I'm only interested in the headline and the date and time of publishing. I need to make quick decisions, and these two are the only thing I need. Now back to the code. Let's create a function fetch news. Inside of the function, we start by creating a request by calling http.newRequest. This function accepts 3 arguments: the HTTP method, the URL, and the request body if any. Here we will pass the constant http.methodGet. And for the URL, let's come up here and create a constant. Back at the function, I will update it to accept an argument ticker of type string. The URL then becomes the URL constant concatenated with ticker. This request doesn't have a body, so I'll just pass nil for the third argument. The new request function returns a pointer to http.request and an error. We check if the returned error is not nil, we just return it to the caller, and let's modify fetch news to return an error type. Next, I need to add a header for the API key. I'll simply do rec.header.add. The add function accepts 2 string arguments, key and value. I will pass the API key header and the API key itself. I want to show you the definition of this header field. I will navigate to the source code by holding the command key and clicking on header here. This brings us inside the request struct. We see the header field is of type header. I will further navigate to the definition of the header type. I can see that the type header is based on a map that has keys of type string and values of type slice of string. And here we can see that the header type defines a method add. I just wanted to show you this use case of type declarations in the standard library. Now, to actually make the request, we first need to create an instance of http.clientType. Then we invoke the do method on client and pass the request. Do returns a pointer to an http.response type and an error. Let's immediately check if error is not nil and return it in that case. The response includes everything the host server sends back to us, including the status code, response size, headers, and of course the response body containing the JSON result. Before we can read the response body, it is good practice to check for a successful status code. So let's do if resp.statuscode less than 200 or resp.statuscode greater than 299, return. I'm gonna use fmt.errorf to return a formatted error, unsuccessful status code received, and I'm gonna pass the status code. The response body isn't of type string or bytes as you might expect. Rather, it is a type that implements the io.readCloser interface. And we use it like this. We'll do json.newDecoder. We'll pass rest.body to newDecoder. This function returns a pointer to a json.decoder type, which has a decode method that I will chain to the output of newDecoder here. Method decode is used to decode the response body into a Go type. Its documentation here states the code reads the next JSON encoded value from its input and it stores it in the value pointed to by v, and v is of type any. So the next step is to create a type that we can use to store the response body. Let me bring up Postman here and let's look at this response body. It's a JSON object which contains three properties: data, includes, and meta. Meta contains information about the response. It shows me the size of the result and other pieces of metadata that are irrelevant to my analysis, so I won't pay much attention to it. The same goes for the includes object, which includes information about news editors. The only thing of interest to me in this response is the data object, and not even all of it. Just properties published on and title within this attributes object. So let's head back to VS Code. I'll first create a struct attributes that has the fields published on of type time.time and title of type string. Now, just because the names of the field match the names of the JSON properties, that's enough for Go to automatically map the correct properties into these fields. But a better practice would be to specify the JSON property using the JSON struct tag, like this. Here we're saying published on field is mapped from published on JSON property and the title field is mapped from title property. This is good practice because it is clearer with no assumptions. And also the struct fields are now independent of JSON properties and can have different names. For example, I can rename published on to publication date and can rename title to headline. I'm happy with these names, so I'll leave them alone. Going up one more level, the attributes are part of another object that is part of the data array. This object has ID, type, attributes, and other properties. As I said, I'm all interested in the attributes, so I'll create a struct and name it seeking alpha news. It will contain a field name attributes of type attributes and will have a JSON struct tagged with the same name. Again, looking one further level up, we see the outer response body which contains the data array. I will model that with a struct named seeking alpha response. It will contain field data, a slice of seeking alpha news, and it has a JSON struct tag data. I can now use the seeking alpha response type to read the response body. Even though it doesn't contain fields for all properties in the response, the decode method will simply ignore any property that has no corresponding field. So I'll come here right above the call to decode. I'll create a variable resp that is an address of seeking alpha news and pass it to decode. Now the response body will be read into this variable. Now we know that the fetch news function needs to return the news, so we could just return res here. But a much better practice would be to create yet another type to represent the news as our program consumes it. Because the seeking alpha news type and all types it depends on That's the Seeking Alpha API's representation, and its only job is to map the return value from Seeking Alpha API to something our program can use. And for the sake of separation of concerns, we shouldn't be passing it around our program. I've explained the separation of concerns principle in more detail in another tutorial that you can find here in the corner. Now I'll go up here and create a new struct named article. It will have a field published on of type time.time and headline of type string. It'll come down to fetch news and update its signature to return a slice of articles and an error. And I'll update these error returns to return nil alongside the error. And down here in the function, create var articles slice of article. I'll create a for range loop to loop over res.data, and inside the loop I'll just create a new variable of type article. Its published on field will equal item.attributes.published_on, and its headline will equal item.attributes.title. Then I'll append this variable to the articles slice. At the end of the function, I'll return articles and nil. Now, back in main and inside of our for loop, after calculating the position, we call fetch news and pass stack.ticker. We'll capture the returned articles in var articles and of course the error as error. If there's an error fetching the news, we'll just log it and continue to the next stack. If there isn't an error, we'll print a login statement found number of articles about the specific stack. I will update the selection struct and add the field articles of type slice of article. In the for loop, I will set the value of articles field to the articles var. And with that, all the analysis is complete, and all that's left to do is deliver the output in JSON format, which is the easiest part of the program. I will create a function deliver that will accept the JSON file path and the slice of selection. It will return an error if the operation fails. The first step is to create the file. For that, we will once again use the os package, just like we did when reading the input file. I'll call os.create. This function creates the file if it doesn't exist. If it exists, it will just truncate it. Create returns a pointer to os.fileType, just like we saw earlier with open, and of course an error. As usual, we check if error is not nil, we return formatted error. And just like before, we will defer closing the file. We've seen how JSON decoder is used to decode JSON into a Go type. Well, now we will use JSON encoder to do the reverse, which is encoding a Go type into JSON. I will create a variable encoder as json.newEncoder and pass the file. I will then call encoder.encode and pass selections. Encode returns an error, so we'll check it and return a formatted error. If all is well, we return nil. Now back in main, after the loop, I'll invoke deliver, passing the output path and the selection slice. I'll capture the returned error and check it. It's not nil, I'll print it and return. And at the end, after the if statement, I will just log print finish writing output to output path. Now to test the program, I'm gonna place this CSV file which has these stack entries. I'll run the program and I can immediately see some output about the news being fetched. This takes just a few seconds loading the news. In the end, we get finished writing output. However, this output doesn't look quite right, so I'm gonna have to stop the recording, debug the issue, and come back and tell you what happened. Okay, found the issue. It's in this line here. Delete func doesn't update the slice in place. I should have reassigned the stack slice from the output of delete func. I've done that here, and I'm gonna rerun again. This time the output looks right. I know it's right because these are the stacks where the gap is more than 10%. I will open up the JSON file here. It's of course unformatted, so I'll right click and select format document. And I can see that we have the JSON output here. I can see the calculated positions, my enterprise, the number of shares, when to take profit, when to stop loss, and below I can see some news headlines along with their publication date and time. This is everything I need to make an informed decision on which stock to trade. If you're wondering why JSON output, well, it's because I display these results in a web page that I built. If you're interested in a web development course, let me know in the comments. Now, as you've seen, loading the news takes some seconds to finish, and this time can get too long if I have more stock entries. That can easily be addressed using concurrency, which I'll talk about next. In programming, concurrency is all about doing multiple tasks at the same time, not necessarily by doing them all at once, but switching between them. This way, the computer can make progress on several tasks simultaneously, increasing efficiency and performance. Modern computer systems from servers to smartphones all leverage concurrency. Go implements concurrency by means of Goroutines, which are lightweight, simple, and safe. Moreover, Goroutines are not mapped directly to operating system threads. A single OS thread can manage multiple Goroutines, which leads to better performance. In this code snippet, function processTransaction prints a message indicating that it is processing a transaction with a given number. Waits for 2 seconds, this simulates a time-consuming task, and then prints a message indicating that the transaction has been processed. Inside of main, we use a for loop to iterate from 1 to 5. And inside the loop, we use the go keyword to start a new go routine for each transaction processing. This means that each transaction is processed concurrently in separate go routine. The main function waits for 3 seconds to ensure that it doesn't exit immediately and allows some time for the go routines to return and complete their execution. If I run this code, we can see processing transaction 2, processing transaction 5, then 4, 1, and 3. Then processed transaction 3, then 5, 2, 4, and 1. And if I run it again, we get a different execution sequence. The go runtime creates threads to execute the code concurrently without our advanced knowledge of any particular order. All we know for sure is that the work is done concurrently. If I remove the go keyword here, I can see processing transaction 1, processing transaction 2, then 3, then 4, then 5, sequentially, unlike with using the go keyword, which is a more efficient implementation. That's it. That's all you need to do to create a go routine. It's that simple. You can also invoke a go routine using an anonymous function. Here I will use the go keyword and invoke an anonymous function which has the same code as process transaction. This is a common pattern in Go where only part of the code needs to run concurrently. So I just wrap it in an anonymous function within the containing function. Another key concept in concurrency in Go is wait groups. Using time.sleep like this isn't a reliable way to wait for Go routines to finish in real-world applications, because we can't know for sure that 3 seconds is enough for all Go routines to finish, and we can't know for sure that it isn't too long of a wait either. A more robust approach would be using a wait group. Here we declare a variable wg of type sync.waitGroup. Before we start the Go routine, we call wg.add1. This increments the wait group counter by 1. Once inside the function, we call wg.done to decrement the wait group counter by 1. This is a deferred call because we want it to be the last thing to be executed before the function exits. Then, after the loop, we replace the call to time.sleep with a call to wg.wait. wg.wait waits for all Go routines to finish before proceeding. And when we rerun the code, we see that we get a similar result as before. Only it is now more robust and reliable. Now, taking all of this knowledge and applying it to our CLI application, we create a wait group right before entering the loop. Once in the loop, we call wg.add1 to increment the wait group counter. Then cut this code and place it inside an anonymous function and use go to make the call a Go routine. Notice that I don't use the loop variable stock inside the Go routine. Instead, the anonymous function declares its own variable s and uses it. In the function invocation, I'll pass the loop variable stock. Once in the function, I defer invoke wg.done. And right after the loop and before calling deliver, I'll do wg.wait to wait for the news to be loaded before I can deliver the results. With that, I'll run the code and you can immediately notice the improved performance. What used to be 10 seconds to fetch the news now becomes 2 to 3 seconds. Another crucially important aspect of concurrency in Go is channels. Channels are a Go data type that provides a way for Goroutines to communicate with each other and synchronize their execution. Channels can be thought of as conduits for passing data between Goroutines. Let's see it in action. In this revised code, process transaction function now takes an additional parameter done. Done is a Boolean channel. This channel is used to send a signal when the transaction processing is complete. In the main function, I create a channel complete using the make built-in function. This channel is used to communicate the completion of each transaction. When starting each Goroutine, we pass the complete channel to process transaction. After starting all the Goroutines, the main function has a for loop that waits for the completion signal from all of the Goroutines. This line here, less than sign hyphen complete, blocks until a signal is received on the complete channel. This loop will iterate 5 times, ensuring that the main function waits for all 5 Goroutines to signal their completion. Once all signals are received, the program prints all transactions processed. Channels are also very useful for transferring data, like in this example. In this code, the process transaction function takes an additional parameter done. Done is an integer channel. After processing a transaction, it sends the transaction number to the channel, indicating completion. In the main function, again using make, we create a process channel, but this time with a buffer size equal to the total number of transactions. This is called a buffered channel. The main function starts a Goroutine for each transaction, passing the transaction number and the process channel. Then it uses range to iterate over values received from the process channel. This is a special use case of for range. We've seen how for range is used to iterate over an array, a slice, or a map. But here we're using it to iterate over a channel. There's no increment parameter for this loop. The loop automatically ends when the channel is closed. And this is how we close the channel. We use the built-in function close and we pass the name of the channel processed. And we do this if the transaction number equals the total number of transactions. This basically says if this is the last transaction, then close the channel. Now let's take all this knowledge about channels and apply it to our stock analysis CLI to achieve the same result but in a different way. In this revised code, we no longer rely on a wait group. Instead, we create a channel for receiving selection instances and it's a buffered channel. Its size is the length of the stock slice, basically the number of the stocks. The other change is that now the anonymous function, besides the s argument of type stock, it also expects another argument that is a selection channel. This channel, we send to it selection instances. Then in the anonymous function invocation, we just pass the selections channel. And inside the anonymous function, all of the code remains the same, except at the end here, we send the variable cell into the selected channel. After the for loop, I move the declaration of the selection slice here because we no longer use it within the for loop. And again, we use range to loop over the selections channel. Inside of the loop, we just update the selection slice with the received selection. Now, in order to close the loop, we just check if len selections equals len stocks. That means we received all of the expected elements in the channel. And now if I run the code, we see that we get a similar result. Concurrency in Go is a truly vast topic, but what you've seen so far is enough for the majority of your concurrency requirements. As promised, we're going to refactor this code and show you how you might structure a real-world application. Let's start with an overview of the folder structure. At the root of the project, we have the main.go file, which contains the main func, which is the entry point of every Go program. We then have a folder named internal and another named pkg, short for package. Let's expand internal. We see that it has other folders inside of it. I'll start with raw. It contains a file raw.go that defines a package raw that provides functionality for working with raw stock data. This is where I move the stock struct. It then defines an interface loader that defines one method, load. Load returns a slice of stock and an error. And this is a common pattern in Go, to name the interface doer and its method do. Further down, we have a filterer interface with a filter method that accepts a stock slice and returns a stock slice as well. The folder package is where I place implementations of the various interfaces, like in the package CSV, where we load the raw stock data from a CSV file. We first define a struct loader that has a field path for storing the file path. Loader defines a method load with the same signature as the load method from the loader interface, and thus the loader struct satisfies the loader interface. And here at the bottom, we have new loader function, which is declared to retain a raw.loader interface type. But its return statement returns an address of the loader struct type. Notice that the loader struct is private and new loader func is public. This is also a common pattern in Go. The consumers of the loader struct don't need to worry about the internal implementation details. All they care about is a type that can be used in place of the interface raw.loader. I also created a private read method with the sole responsibility of reading the CSV file. And instead of returning a slice of string, I created a type alias columns that is a slice of strings, and another type alias rows, which is a slice of columns. This makes the code a little bit more readable. I hope from this you can see the benefit of using interfaces. They make the code more scalable and maintainable. For example, if I need to change the implementation to load stocks from the web instead of a CSV, all I'd need to do is create a new struct type that satisfies the load interface and use it in place of this one. This minimizes the code that needs to be changed, thus minimizing the chances for introducing bugs. They also provide better code organization and separation of concerns. The consumer of raw.loader doesn't and shouldn't care about how the data is loaded. I made a whole tutorial explaining these concepts in detail. I'll leave a link to that below the like button. Next, we have a folder process that contains a file filterer.go. As you might have guessed, this is where the implementation of the raw.filterer interface lives. In the previous version, this filtering was done inside of the main func. However, I think it is reasonable to have a separate interface and implementation, for the simple reason that if my filtering criteria changes, the code changes would be contained in a small part of the project. Back to the internal folder, we have a package POS, short for position, which provides functionality for calculating the trading position. This is where I move the position struct and define an interface calculator with the method calculate. Calculate returns a position instance. The implementation of this interface lives in the process package in the calculator.go file. We start by declaring a struct calculator that defines two fields, profit percent and max loss per trade, both float 64. These were package variables in the previous version of this solution. The calculator struct implements the pos.calculator interface via the calculate method, which has the same code as before. New calculator is a constructor function that returns a new instance of calculator. Back to internal, we define a news package that is all about fetching stock news. This is where the article struct is defined, and this is where I define a fetcher interface with a fetch method. As you can see, this interface and struct are independent of seeking alpha and have no knowledge of its existence. All they do is define what is news and the parameters for fetching it. This is great because, as explained earlier, it makes the solution scalable in case I need to use a different news provider. Now the fetcher interface is implemented here in the salpha package in the seeking_alpha.go file. We have a client struct with the fields base URL and API key, both of type string. Client implements the news.fetcher interface via the fetch method, which has the same signature. At the bottom of the file, we have the new client constructor function, which returns a new instance of the Seeking Alpha API client. Now, there's a little bit more going on here. I've changed the implementation of fetch from the previous version to show some common techniques for building an HTTP client. First, note that we now have this buildURL private method that returns the URL to be used for creating the request. Previously, we just used the URL const concatenated with the ticker and used it to create the request. Build URL starts by parsing the base URL. This way of building the URL ensures that the URL is well formed and encoded properly. It handles any special characters in query parameters automatically and prevents common mistakes in URL construction. It is also safer. Directly concatenating strings to form URLs, as done in the initial implementation, can lead to errors or vulnerabilities, such as URL injection attacks, if the inputs are not properly sanitized. We then set the path of the parse URL to the remaining Seeking Alpha URL path. This ensures that the path is correctly appended to the base URL. We also use URL.values to add the query parameters, encode them, and set the encoded string to the raw query property. This ensures that the query string is correctly appended to the base URL, respecting URL encoding rules. This way of building the URL is a good practice that is especially important when URL is coming from user input. Besides moving the parsing of the response body into its own method, the rest of the code remains pretty much the same. Going back to the internal folder, I added a folder named trade that contains package trade. I moved the trade struct into this package, and I defined an interface deliverer with a method deliver that delivers the stack selection. Once again, this interface has no knowledge or concern about the delivery medium. It just describes the intended behavior. Deliverer is implemented in the package JSON in the package folder. Here I declare a struct deliverer that has a field file path. Deliverer defines a method deliver that has the same signature as that of the interface method and had the same code we used earlier in the previous version. The constructor function newDeliverer returns an instance of the deliverer struct. I now want to turn your attention to this CMD folder, short for command, which is where you would typically find a file for each command in a command line application like this. This application has only one command, so we only have this root.go file. The run function contains pretty much the same code we had in main in the previous implementation. Run doesn't declare nor accept as input any concrete implementations. Its arguments are all interface types: row.loader, row.filterer, pos.calculator, news.fetcher, and thread.deliverer. It then calls these interface methods to perform the various tasks that main used to perform. Again, this is a better architecture and it's more scalable and maintainable. If any implementation in loading stacks, loading news, filtering stacks, delivering stacks changes, this method does not need to change and doesn't care. Only the specific implementation is amended or replaced, and this function doesn't need to be modified. Now let's take a look at main. Main now acts like the maestro who conducts the orchestra. It is here that we declare the concrete implementations. We first define a variable LDR of type raw.loader and assign it csv.newLoader and pass the input path. Similarly, we declare a variable of type raw.filterer, pos.calculator, news.fetcher, and thread.deliverer, and assign the values of those to the concrete implementations we've just went through. We pass these variables to cmd.run and invoke it. We check if there's an error, we print it. Then call os.exit and pass 1, which causes the program to exit with a status code 1. I want to improve the app so that it accepts input rather than hard coding the options like we've been doing. One way of passing options to a command line app is by using flags. I want to be able to accept the input path as a flag and I want it to be required. In addition, I want to accept the account balance as a required flag. Also, I would like to be able to accept optional flags. I want to add flags for the output path, loss tolerance, profit percent, and the minimum gap. Optional flags have default values that can be used when the user doesn't provide anything. I'll declare input path equals flag.string. I'll pass to the string function I, an empty string, and the string path to the input file required. What this means is the program expects the flag I. I is a string. Its default value is an empty string, and its help information or description is the text path to input file, parentheses required. This function string will return a pointer to a string, and we're capturing that return value in the variable input path. The flag's data type string, and its default value is an empty string, which is the zero value of string. This is enough to tell the runtime that this is a required flag. Similarly, this next line is saying expect a float64 flag named b. Its default value is 0.0 and its help text is account balance between parentheses required. Again, since the default value of the flag is 0.0, which is the zero value of float64, this indicates that it's the required flag. The next lines declare the optional flags. They are treated as optional because they all have default values that differ from their type's zero value. Output path O, a string with the default value ./opg.json. Loss tolerance L, a float64 with the default value of 0.02. Profit percent P, a float64 with the default value of 0.8. And lastly, min gap, a float64 with a default value of 0.1. We then call flag.parse to parse the passed flags. I then check if input path or account balance weren't provided. We call flag.printDefault to print the usage information of all flags and exit with the code 1. Here's how that would look like. Notice that I had to dereference the variables because, as I mentioned, these flag functions all return pointers. One last thing I want to show you before running the program is how to use environment variables in Go. The seeking alpha URL and API key are perfect examples of storing configuration information as environment variables. We simply call os.getInv and pass the key of the environment variable. GetInv returns a string containing the value. We capture it in the variables seeking alpha URL and seeking alpha API key. I'll first validate that these values are not empty and then pass these two to salpha.newClient function. With that, we can rerun the application after refactoring. I will actually build the app first using go build-o opg. I will run the binary opg without specifying anything. As expected, I get the error missing seeking alpha URL environment variable. I'll just set both environment variables using export. If you're on Windows, this is how you would do it. I will run again, and this time I get the program usage explaining which flags are required and which are optional. I will pass the I flag and the B flag and run. And we get the result we expect. I will rerun, but this time I will pass 0.2 for the N flag and run. This time I only get one stack since I'm saying I only want stack with a gap equal to or more than 0.2. Earlier in this tutorial, I told you that I won't reveal how to register for seeking alpha and generate an API key. That's because if hopefully hundreds of thousands watched this tutorial and all of them follow along with the code, I don't want all those people hitting Rapid API and burning their servers. That is why the next project will be building a web server that we can use in place of seeking alpha's Rapid API. In this tutorial, we'll build a web server that serves a REST API to handle requests for news about a particular stack. We'll also implement functionality for saving news articles. We'll first build a solution using only the standard library. Then we'll utilize a popular third-party module called SheRouter to extend the functionality a little bit. We'll use the net/http package to build the web server. Here's how. This call to the function http.handlefunc registers the route slash news slash v2 slash list by symbol with the handler get articles. An HTTP handler is nothing but a function that accepts two arguments. The first argument is of type http.responseWriter and the second is a pointer to http.request. Any function that satisfies this condition can be used as a handler. The end result of this call is that whenever this URL path is visited, getArticles function is executed. Before starting the server, we print server listening on port 8080. Then we start the server by calling http.listen and serve. This function accepts a network address as the first argument. This value, colon 8080, means listen on the local host on port 8080. The second argument is of type http.handler, which I'll talk about in a bit. But here we're passing nil, which means use the built-in handler. We capture the error returned by listen and serve and just log it as fatal, because if we can't start the server, then this is pretty much a fatal error. But all goes well, we shouldn't have to worry about this error. Now, inside of getArticles is all the logic needed to serve the request to getArticles. The http.request instance contains all the information in the request. The request's HTTP method, the URL, the query string, the body, headers, and so on. We first check if the user is authenticated. We extract the API key using r.header.get, passing x-rapid API-key. This gives us the value of the API key that we pass to this validation function. It's beyond the scope of this course to go into details about authentication techniques, so this function just compares this API key to a fixed value and returns true if they match. If authentication fails, we call http.error, passing the responseWriter instance w, the error description, invalid API key, and the constant http.status unauthorized, which is the number 401. Error replies to the request with the specified error message and HTTP code. It does not otherwise end the request, which is why we do a return. If we don't, the function execution will continue, which leads to anomalous behavior. We then check if the request method is anything other than get. If that's the case, we call the http.error function, passing the responseWriter instance w, the error description, invalid request method, and the constant http.status method not allowed, which is 405. Then we extract the stock symbol ID from the query string using r.url.query.get and pass ID. Following good practice, we validate the input by checking if ID is empty. If it is, then we call http.error, once again passing the responseWriter instance w, the error description, ID is required, and the constant http.status bad request, which is 400. We then extract the size query parameter, and since it is extracted as a string, we convert it into an int. I'm not checking the returned error because I'm setting a default value for size anyway. With these two variables, we can now call getArticles function from the db package. This function doesn't call a real database server. Rather, it loads some dummy data from this JSON file. We check if there's an error. We call http.error, passing the responseWriter instance w, the error itself, and the constant http internal server error, which is 500. Now, getArticles returns a slice of this article type, but as we've seen, the expected output is a different type. So here, I've defined the type, article response, and its associated types. And in the handler, I'll create this variable of type article response. Then I'll use a for range loop to populate the response variable. Lastly, we use w.header to set the content type to application/JSON. To send back the request, I create a JSON encoder using json.newEncoder and pass the responseWriter w and then invoke encode and pass the article res variable. Notice that once again we use JSON encoder. This time we pass the responseWriter. New encoder expects an io.writer type. which says response writer satisfies. So we can pass it to encoder here. This is just another example of the great use of interfaces in Go to accomplish polymorphism. Now to test this, I'll run the application using go run dot. It tells me that the server is listening on port 8080. Bring up Postman here. For the URL, I'll use localhost colon 8080. Then the URL path /news /v2 /display symbol. ID equals AAPL and size equals 5. Head over to headers and add the API key. Hit send, and this returns result in a schema that is not identical to that of seeking alpha, but my OPG analysis CLI would be happy to consume. So I'll head back to the CLI and set the seeking alpha URL environment variable to localhost 8080 and run the CLI. And we can see that it still works like before. The only difference is here we get 0 articles for the stock symbol AVGO. But that's okay because I didn't provide dummy data for that symbol. One more thing I quickly want to show you is to create an API endpoint to save articles. Back in main, and make one more call to http.handlefunc to register the root news/v2/save article. And the handler for that is the save article function. Save article starts by validating the API key. In a real world application, you might also validate that the caller has permission to add articles. Then validates that the request method is post. Then it uses JSON decoder to decode the request body contained in the field r.body into a variable of type db.article. We then call db.saveArticle and pass the article object. We then check if that returns an error. If so, we respond with a 500. Otherwise, we return the saved article to the caller. I want to quickly show you the save article function, which again doesn't save an article to a real database. It rather appends it to the JSON file that contains the dummy data. Particularly, I want to point out the functions JSON.unmarshal and JSON.marshal. JSON.unmarshal is used to parse a JSON data and convert it into a Go data structure, such as a struct or a map. Here, we're using it to convert the file content, which is in JSON, to the Go type slice of article. The term unmarshal in Go is equivalent to the term deserialize or parse in other languages. JSON.marshal is used to convert a Go data structure into JSON format. And here we're using it to convert the slice of article back to JSON before we can save it in the file. The term marshal in Go is equivalent to the term serialize in other languages. We've seen the method JSON.decoder.decode previously, and it uses unmarshal under the hood. And conversely, JSON.encoder.encode uses marshal under the hood. I will now rerun the application to test a new endpoint. Bring a postman here, add a new request, and change the method to post. I'll set the URL to the URL of save article. I'll add the API key header, and for the request body, I'll use I'll use this date and time, and for the headline, I'll just say Visa is brilliant and hit send. I'll come back to VS Code and open up my articles.json file formatted. Right at the end, I see the new article entry. As you've seen, the standard library comes equipped with the net/http package, which is capable of creating and serving a web server. However, I want to show you a popular third-party library called Chi that provides more functionality and makes life just a little bit easier when it comes to building REST APIs. We start by adding the module using goget github.com/go-chi/v5. I'll then come up to my main function here and declare a variable r equals chi.newRouter. To add the get endpoint for fetching the articles, I'll call r.get and pass the route pattern and the handler. This time I want to change the route to API/v1/articles, just to comply with REST best practice. And for the handler, I'll pass the same function getArticles. As for the post endpoint, I'll do r.post I'll pass the same route and pass save article for the handler. Then I'll update the call to listen and serve and pass R as the HTTP.handler instead of nil. Now listen and serve will use the key router as its HTTP handler rather than the built-in one. I'll run the program and I'll hit the postman to test the new endpoint, and I see that it returns the same result as before. As you can see, key router doesn't replace the core functionality of the net/HTTP package, it rather complements it. First of all, when adding the routes, it's clear that this is a get route and this is a post route. It's also now possible to have the get and the post routes to have the same route pattern, which is common in REST. Also, now we don't have to check for the request method inside of get articles and save article. Key will perform that task under the hood for us. And we can safely remove this code. I'll actually leave these functions alone. I'll duplicate them and rename them. Get key articles and save key article, and remove the method verification code in these. I'll then update the routes to use these new functions as handlers. And just quickly, I'll run the code and bring a postman and verify that everything still works. Beyond this, Key also gives us the ability to add middleware. Middleware are handlers executed before or after the main HTTP handler to perform various tasks, such as logging, error handling, or request modification. I'll show you how. I'll come up here and add 3 calls. r.use middleware.requestID, r.use middleware.logger, r.use middleware.recoverer. Request ID is middleware that generates a unique ID for each request. This is extremely useful for tracing and correlating logs for specific requests across our system. Logger middleware logs the start and end of each request along with some useful information such as the request method, URL, response status code, and the duration of the request. Recoverer is middleware that recovers from panics anywhere in the chain. It prevents the panic from crashing the server and logs the panic message along with the stack trace. It then returns an HTTP 500, which is internal server error status, to the client. With these changes, I'm gonna rerun the program and call the get endpoint from Postman. Now, if you look at the terminal, you'll see this very useful information. You have the date and time the request came in, the request ID in yellow here, the request method and full URL, the IP address where the request originated, the returned status code, the response size, and the duration of the request. These are extremely helpful information. When debugging a problem with any system, the logs are usually the first place to start. And since these logs are output to the standard output, they can be stored in a log storage for future use. We're not limited to only built-in middleware. We can build our own. A good example would be moving this code that does the API key validation into a middleware function. This would be cleaner and more maintainable than duplicating the code like this. To do this, I create a function and name it API key validator. For a function to be used as middleware, it must accept an input argument of the type http.handler, which is an interface, and return a value of the type http.handler as well. It's a common pattern to name the input argument next, but it's not required. API key validator returns http.handlefunc. Handlefunc is a type declaration that satisfies the http.handler interface. It is a function that accepts 2 arguments. The first argument is of type http.responseWriter, and the second is a pointer to http.request. Just like getArticles and saveArticle function, with just a small difference that I'll show you in a moment. But inside this anonymous function is where we place the API key validation code. The variables w and r give us access to the response writer and the request, and basically allow us to do anything with the request and response. After all the logic, we must call next.serve_http, passing w and r. This call is what allows Key to chain multiple handlers like we've seen. Otherwise, the execution stops here. Now we can safely remove the key validation logic from our 2 functions. Then I'll come down at main here And just like any other middleware, I'll do r.use API key validator. With this change, I'll run the code and call the endpoint again. It still works just like before. And to prove to you that the middleware is working, I'll remove the API key header and send the request again. No surprise, it fails with a 401 status code. These were just some of the features of the key module. Feel free to go over the documentation and see what else you can do with it. Let me know in the comments what you found most interesting. And with that, we come to the end of the course. I hope you learned a lot and enjoyed along the way. So where do you go from here? Well, this is just the beginning of the journey. I encourage you to code, build small projects, contribute to open source projects, and continue learning. I left more learning resources in the description of the video. Also, I plan to publish more Go tutorials, so if there's something specific you want me to cover, be sure to leave that in the comments below. And be sure to subscribe to the channel for more content. Thank you for watching, and I'll see you in the next one.